All right. Good morning, everybody. It's 8 o'clock. We're going to go ahead and get started today. Um, Thank you for joining us. We are here. We're going to be talking about PFAS treatment. It's a technical training for engineers. Um, I'm Sarah Conrad. I'm a technical assistance grants project manager in the Arizona Department of Environmental Quality's drinking water section. And we'll just go over the agenda quickly this morning. As you can see, we've got two speakers lined up. Tom Speth from EPA. He'll be giving the first two presentations. Then we'll have Yasmina Markovsky from ADEQ. She's got about 2 hours of a presentation, so we'll take a break as close to 10 o'clock as we can, about 15 minutes. And then we'll continue with Yasmina's presentation, and we'll save some time for question and answers at the very end, and we'll finish at noon. A couple of housekeeping items before we get started. You can find the agenda for today and the PowerPoint handouts. They're located in the handout section. You see those next to the orange arrow on the screenshot there. Your webcams are disabled and you're all muted. If you do have any questions, please use the questions bar on the right-hand side. That's down by the green arrow. You should see that on your pop-out. And if you have any technical issues, please send me an email or give me a call. My contact information is at the bottom of this slide. All right. We do have two poll questions to gauge our audience experience level. Hannah, do you want to go ahead and launch the first? We'll leave these open just for a minute or two until we get about 75% of you voting or so. All right. All right. Looks like we got pretty good breakout. Most people are saying little experience, about 25% moderately and 27% no prior experience. So that's great. I think that's helpful for Tom and Yasmina to know this morning. Would you go ahead and share our second one, please, Hannah? Our second poll is, are you working with the community on PFAS treatment, either currently or in the past? All right. Looks like we got almost 90% voted, so let's go ahead and see what our, we've got about 39% said yes and 61% said no. So also very good information for Tom and Yasmina as they. With that, I'm ready to introduce our first speaker. I'm just going to switch um, presentations here. Sorry about that. So Dr. Thomas Speth serves as Senior Science Advisor for the US EPA Central for Environmental Solutions and Emergency Response, where he is leading efforts on PFAS, lead, and small water systems. He is a professional engineer who has worked in the field of water treatment research at the US EPA since 1986. Over his career, Dr. Speth has been active in numerous organizations such as the American Water Works Association and the Water Research Foundation, where he has served as trustee, chair, and EPA liaison on numerous divisions, committees, and advisory boards. All right, Tom, I'm going to turn it over to you and just let me know when you'd like me to advance the slides.
Yeah, can you hear me?
Yes, we can hear you.
Okay, great. Thank you so much. Yeah, so I'm very happy to be here. We found a way to get this done. In years past, DPA used to use GoToWebinar, but then they stopped and they're not supporting it anymore. So unfortunately, I have to call in via phone, but we've worked out a way to do it. So hopefully it won't cause any problems with feedback or whatnot. So let me know if there's an issue. So yeah, so I'll be giving two talks. One is on centralized treatment, and then one is more on the residual side of things, and and more advanced technologies. I might run a little longer on the centralized treatment talk, but I can guarantee you I can finish up by about 9 o'clock. So the totality of the two talks will be about 55 minutes. Next slide, please. So I just want to acknowledge my co-authors. These are other EPA employees that are working in this area, but actually there are a lot more than this. These are some of the more PI people in our group, and I'd like to acknowledge them. Next slide, please. Okay, so this is the standard, how to remove PFAS from drinking water. So the contaminated water comes in and it's treated at the drinking water facility. And there are three technologies that are generally effective that the states will be, permitting for direct drinking water treatment: anion exchange resins, granular activated carbon, and reverse osmosis membranes. And we'll get into these a little bit more, but frankly, all the technologies are more effective for the longer chain PFAS than the shorter chain PFAS. And the removal efficiencies, especially for anion exchange resins and GAC, are a function of the source water characteristics and also the system design and operation. Now, each one of these technologies too will have residuals, whether they be spent media or liquids in case of the RO concentrate, and they need to be addressed in terms of what you need to do with them. And of course, the PFAS is on the spent resin, and it can be regenerated. These resins and the GACs can be regenerated, landfilled, or incinerated, and hopefully with no releases of PFAS. So when I say regenerated, I mean the reactivation of GAC. Generally, the anion-exchange resins that are used are single-use resins, and they are either landfilled or incinerated. GAC has an opportunity to be reactivated. And then for the RO concentrates, there's really no plug-and-play technology for treating RO concentrates. So I'll get to that a bit in my second presentation, and we'll cover that a bit more. So next slide, please. This is for those that are just popping into the area and want to have a database of what's in the literature for PFAS removal. So US EPA has a treatability database. If you click on the link here, if you have the PDFs of these slides, or just contact me. Or actually, if you just Google EPA TDB or treatability database, it pops right up as like the first thing that comes up. And it's a database that has literature information on over 140 regulated and unregulated contaminants, and that includes PFAS. So there are numerous PFAS that are in there. I think we're up to 69 different PFAS from 201 references. So if you're interested in perusing the literature for PFAS removal, I'd recommend going to this database. It's all there, and we update it yearly in terms of what's out there in the literature. Next slide, please. Okay, so what do we find in the treatability database? The ineffective treatments are the conventional treatments, low pressure membranes like MF or UF, biological treatment, which includes slow sand, disinfection, oxidation, and advanced oxidation. What are effective, as I mentioned before, is ion exchange resins, high pressure membranes, reverse osmosis or nanofiltration membranes, and then activated carbon, particularly granular activated carbon. However, it has to be designed for removing PFAS, which means it has to be replaced or reactivated in a timely manner based on breakthrough. If you put in a bed for, say, taste and odor removal that you're only replacing every 5 to 8 years or something along those lines, very shortly that bed will be exhausted and will be ineffective. So it would have to be a deep bed design for PFAS removal. Powdered activated carbon is an interesting application, and it's probably more just effective for select situations. Um, we know that if you want to remove, say, 50% removal, the pack dose would be about 60 milligrams of powdered activated carbon per liter, which is a reasonable dose of pack to add to a drinking water facility. But if you wanted to get up to 90% removal, and these are even with some of the better PACs, you'd have to add like 50 milligrams per liter of powdered activated carbon, which is really difficult for a utility to do in terms of handling the carbon and the sludge and things along that line. So, but if you're just above the MCL and wanted to drop it down, say 50%, it could be an option. And there are other packs out there too. If you go to the literature, you can find like super fine packs that could be used that increase the kinetics of absorption, and you get better results because it takes it out quicker and through your process, and your ultimate capacities are higher. But there are some literature out there on this issue. Just a little bit. Next slide, please. Just a little bit about what is absorption and how it's handled. And for those of you that are fairly well versed in this, this is a little background. But you've got the granular activated carbon particle here, which is the blue particle. And the flow envision it as the flow coming down from top to bottom, and it's going past this particle. And what you have is there's always a stagnant film layer around every particle in a bed. And so the PFAS has to diffuse through that stagnant layer, and we call that film transfer resistance because there's a certain amount of resistance there. And then once it gets into the particle, it has to diffuse into the particle through the pores. And so there's another resistance there. And so instead of getting a breakthrough profile that's perfectly steep, as shown on the green on the right side, you get a breakthrough profile that's more of a classic S-shaped curve. And that kind of S-shaped curve is caused by these resistances to absorption. So it doesn't immediately get to the ultimate capacity of the carbon. And then as this is all going on, you can have competition between different adsorbents, natural organic matter that's present that can block the pores or preload onto the carbon. One could even see biological films growing on the outside of the carbon if it's been in place for a fair bit of time. And also at the top part of the carbon, if you're having iron and manganese issues, you can actually plate out iron and manganese on the top part of your bed, which can cause you problems. And hopefully you won't have to backwash. But those are some of the factors that come into play. Next slide, please. Slide 7. For ion exchange, it's a different animal in terms of you're looking at PFAS, which is negatively charged. The positively charged sites on the ion exchange resin have chloride attached to them. That's generally how it's done with PFAS removal. These medias, the single-use medias, were originally designed for like nitrate removal and then modified for PFAS removal. And it's initially loaded with chloride. And then as the water comes past the particle, the PFAS exchange with the chloride is released. And because the PFAS is very low concentrations, the amount of chloride released is very negligible. However, you can have other constituents like nitrate and sulfate and organic matter that exchange with the chloride also. And so you can have some competition with the absorption. And it depends on what concentrations those are and then what comes into play. But the big ones to look out for are nitrate and natural organic matter. They've shown to be a good or a bad, if you look at it that way, competitor against PFAS absorption with PFAS selective resins. Next slide, please. Okay, so what affects PFAS removal? And so here is, I've mentioned these things a bit, and there are a lot of things that can affect removal, and this is a laundry list you can go through in your own time. But the contaminant, which PFAS it is a big issue. What concentration it is, and what adsorbent you choose are big things. Along with, you then have to handle hydraulic loading rate and column size and system operation, whether it's parallel, series, or lead lag operation. All these things come into play, and they can affect the capacity of the carbon, or they could affect the kinetics in terms of, either seeing it earlier breakthrough or later breakthrough base. And if you remember that S-shaped curve, even though your ultimate capacity could be quite high, if that slope is really low, you could get some initial breakthrough if not designed correctly. Next slide, please. Okay, here are some more in terms of background water quality. The inorganics, natural organic matter, as I mentioned, is a big thing because it can affect in a number of different ways. It can affect the capacity, and can it also affect the preload. It can preload onto the media and block pores and cause issues that way. And other things can come into play also, and I list them just for the sake of if you're running into issues, it can affect the absorption. For instance, temperature is an issue you usually just can't get around, but for GAC works better in colder water than warmer water, just because it's an exothermic reaction, and it favors absorption in colder waters. Next slide, please. So a little bit about GAC and ion exchange and kind of how the two compare. So the granule activated carbon, empty bed contact times typically range from 5 to 20 minutes, depending on what needs to be done. And the hydraulic loading rates are usually around 4 gallons per minute per foot squared, or 10 meters per hour. And so those are the standard kind of designs. Ion exchanges usually has a much lower empty bed contact time, 2 to 7 minutes, and it has a much higher hydraulic loading, up to 8 gallons per minute per foot squared, or 20 meters per hour. And so what you see is that some utilities that are very space limited ion exchange could be a good option for them if they just can't afford like putting in another building, or if they don't have the floor space. And some utilities see ion exchange, assuming that ion exchange works for their mixture of PFAS and their water quality, and they're also integrating into their current system, making sure that all works out correctly. Ion exchange has that benefit of being a much smaller system physically. And so, however, you should be careful about choosing between the two, because out there in the literature, there's a fair bit of stuff out there saying one is better than the other, just because it has a higher capacity. And that's generally not true. It doesn't have to be true, because granule activated carbon is much cheaper in terms of cost. And in many applications, it can be the optimal choice. So one would have to look at it fairly closely to see which is best for any given utility. Okay, next slide, please. So a little bit about the advantages of each technology. So GAC is the most studied technology. So there's a lot of literature out there on GAC treatment of PFAS. It is it's a non-steady state process, so it will remove 100% of the contaminants for a period of time until breakthrough. It has good capacity for some PFAS, such as those heading toward potential regulation. What is in green here are some of the secondary benefits of GAC. So it will remove a significant amount of disinfection byproduct precursors material. And because of that, you won't have to use as much chlorine in your water, or your disinfectant into your water. And so it helps with maintaining residuals. and it likely has a positive impact on corrosion because you can handle your residuals out into your distribution system a little easier. And also, and this is a point that utilities that we've run into, one of the reasons they use granular activated carbon is it can remove other co-contaminants that might be present with PFAS, such as pesticides, SOCs, and other contaminants. Many hydrophobic contaminants are absorbable onto GAC. For anion exchange resins, and these are the PFAS selective resins, like GAC, they can remove 100% of the contaminants for a time. As I mentioned, it has a higher capacity. It has a high capacity for PFAS and a very higher capacity compared to GAC, and hence it has a smaller footprint compared to GAC. And one of the secondary benefits is if it's an anion, another anion contaminant, it could help with removing select co-contaminants or nitrate or something along those lines. With high pressure membranes, of the three, this is more of a steady state process, but it has very high PFAS rejections, fairly much across the board for all the charged PFAS. And it will remove a lot of other co-contaminants and also disinfection byproduct precursors. And therefore, it will be help with maintaining disinfection residuals through your distribution system. Issues to consider with these three technologies thank you, next slide, are that for GAC, reactivation frequency can be very short in some instances, and a utility may find that it's just not functional to every month or two having to exchange a bed. Logistically, it would be a challenge, and it also indicates that it would be very costly in that instance. With GAC, you can get potential overshoot of poorly absorbing PFAS, and so the weaker absorbing PFAS can be chromatography. Oh my heavens, I've said this my whole career and now I can't say it today. It can be pushed forward by more strongly absorbing PFAS, and what you see is that you can actually get a concentration in your effluent higher than what's in your influent, and that can be disconcerting. And so you'd have to keep track of that and make sure that that's not going to cause you a problem if that PFAS is a regulated contaminant. Backwashing for PFAS shouldn't be an issue because the bed stratifies. You wouldn't want to backwash a lot. Usually this is a deep bed absorber after a particulate removal, after sand filtration. Hopefully you won't have to backwash, but you can backwash and it shouldn't be a problem. Also, the disposal and backwashing, when you backwash, the PFAS won't desorb off the carbon that fast. And so it will, if you spend a long time desorbing, but during backwash, you shouldn't have to worry about it coming right off the carbon into your backwash water. There'll be a little bit of PFAS in your backwash water due to what's on top of the bed, with your headspace above the bed and through interstitial spaces between particles, but you won't get it back off the carbon. And also, you have to consider your disposal or reactivation of the spent carbon. For anion exchange resins, the replacement frequency can be short. The media is more expensive than GAC, and like GAC, it can have overshoot of poorly absorbing contaminants. Some of the issues that the initial flushing you may have to consider based on your utility. You'll want to blend waters. If you only have one column, you might want to flush your column to make sure you're not going to get some water initially coming through your system that is corrosive, but it shouldn't be an issue. It can be largely handled fairly easily, and resin manufacturers will offer a buffered resin to help alleviate that problem if you only have one bed and you're concerned and you have issues regarding that disposing of that initial flushing. There's unclear secondary benefits in terms of removals of other contaminants that really hasn't been looked at too much, and because it's just anion exchange, it will be fairly limited. But but there could be, but it hasn't been studied that much. And of course, disposal of the resin is an issue. With regard to high pressure membranes, capital and operating costs are huge. Membrane fouling can be an issue, especially for systems treating surface waters. It tends to foul much more than groundwaters. And one would have to take into account corrosion control. Often we've seen systems that have put in membranes for, say, nitrate removal or softening, and now they have PFAS in their water also, but when they design for nitrate or softening, they're bypassing, say, 20% of their water stream. And so one would have to, perhaps they might have to treat that bypass stream, say, with a resin or a GAC, if the MCL and the concentrations fall a certain way. So something to keep in track of. And then there's a lot, there are issues, and we'll get into these a lot in the next presentation, but there's somewhat of a lack of options for concentrate treatment and disposal. Next slide, please. Here's a publication that just to give you a feel for where PFAS are. This is a rough correlation, and it's a rule of thumb kind of thing. We've often heard that longer chain PFAS absorb better to GAC than shorter chain PFAS. We've looked at it in terms of what the characteristics of the PFAS are in terms of solubility and molecular weight and density and parameters such as that, and worked up a correlation that gets away from the chain aspect, because you can have ethers within the chain, or it could be a branch chain, and that rule of thumb is very limited. So we looked at 428 PFAS with this correlation, and looked at where they fall in terms of absorbability, and usually somewhere around cis-1,2-dichloroethene is considered a contaminant that can be removed with GAC. And so when you plot up the PFAS, and I listed the PFAS that are heading toward proposed regulations on the bottom of the curve. They're listed, and you can see how they're removed. But the take-home message on this slide is that if you're looking at a huge range of PFAS, and this correlation could be used for even more PFAS than the 428, but if you're looking at a huge range of PFAS, carbon will not remove all PFAS. There will be some PFAS that are very weakly absorbing. The good news is that they're not regulated, and we don't have any health information regarding them, most of them. But it will remove 76 to 87% of the PFAS we've looked at. So it's a very good technology, but it's not necessarily spot on. And we know of some PFAS that are difficult to treat with GAC, such as PFBA and others that come through very quickly. Next slide, please. And here's just a little bit about that chromatographic behavior in terms of PFAS. This one lists some SOCs that we've done in years past. And you can see how some of the weaker absorbing ones, the ones that break through early, say the ones in red, and you can see concentrations above their initial concentration. And that could be up to maybe even up to 50 to 100% higher. That is something that you'll want to keep track of. One thing to note is for the non-regulated PFAS and the PFAS that are not necessarily, or other contaminants that aren't a health concern, one can model these breakthroughs with the current models, and then that gives you a much better feel for what the competitive effects are in your water, and you're able to model the expected breakthrough of your more strongly absorbing PFAS that we are concerned about, and it is very helpful for utilities, we're finding. And if you ever need help with that, let me know. A little bit about column configurations. Single columns are often used. However, you lose some of the potential absorption capacity on changeout, because you can't run it. You can only run it as long as you're below the MCL. You can run staged parallel systems where you start the systems at different times, and therefore you can run the first bed out longer because while that may be above the MCL, you're blending it with water from other columns that are below that are at zero, and you can maximize your GAC capacity on the first column before you take it off to reactivate it. And then lead lag systems are systems where you have two in series. You fully load the first one or as much as you can. The second one is catching the PFAS before it gets to the distribution system. Once the first column reaches its high capacity, you then take the second column, make it the first column, and you add a fresh column on the back end as your second column, and you just keep rotating along those ways with valving so that you can, again, maximize the PFAS absorption capacity. Here's an example of something we've done. It was a utility down in Georgia that we helped out. At the time, the MCL was 70, and they had some sand filters that they were thinking of putting as emergency treatment, either 18 or 24 inches of carbon on top of those sand filters. So we did a little bit of modeling for them, showing how long each of those beds might last for them before they'd have to change it out. And you could, if you were removing all the beds, if you ran all 10 beds at the same time, you could get 162 days or 217 days. But if you ran 10 total beds where you're blending, that would be the example on the right, where you're blending waters and you're just keeping it below the 70 parts per trillion in this case. And you could hopefully then you could get much more days, such as 360 and 480 for all filters when you start working up the capacity. So just an example of how you could benefit. It also shows that when you're blending, you are moving your PFAS through your system and putting it in the effluent, where if you just ran one column or all the columns at the same time, you get a time where there's nothing coming through your system. So something to take into account. Okay, let's talk. Next slide, please. I'm sorry, I think I missed the next slide, please, a couple times, so I apologize for that. Next slide is the high pressure membrane slide 17. And that is high pressure membranes use pressure to push water through through a membrane. You're fighting against the osmotic pressure. And the good news is that RO membranes, or very tight nanofiltration membranes, are very effective for rejecting PFAS. And so one can have some advantages compared to this, as the adsorbent, which is on the right side, which is a non-steady state where you have to keep track of it. RO membranes will give you largely a consistent water product as long as your membranes have retained their integrity and you haven't had issues with regard to that. Next slide, please, slide 18. So as I mentioned, PFAS rejections are very high, but therefore our reverse osmosis and nanofiltration membranes, ultrafiltration and microfiltration, which are used for particulate removal, do not give you PFAS rejection. And so the membranes will follow over time, and most systems will add an anti-scalant to prevent fouling or keep it at bay for a period of time. And a utility will likely have to do periodic cleaning with a detergent / acidic or alkaline solution based on what's following their membrane. And that surface waters, as I mentioned before, follow to a much greater degree than groundwaters. Next slide, please, slide 18. So just a touch on drinking water cost models the EPA has on their system available to you. You can get this link, or if you have questions, get a hold of me. I'd be glad to talk to you about it. there are so, next slide, please, slide 20. So there, for instance, on granular activated carbon, there's a huge number of construction operational issues that one must take into account for costing, and I'm not going to go through all these. This is a slide that basically says here they are, plus there are over 300 additional design parameters you have to take into account. A lot of these are automated within the cost models, so it does help you out a bit that way. But the main ones listed here, you'll definitely want to have information on before you go working on those cost models. Next slide, please. And here's slide 21 is a slide for ion exchange, and similar in that all the issues that I've talked previously about, you need to know information about those before you'd get into costings. And the next slide, slide 22, is for high pressure membranes. So the take home on these three slides are know what you're getting into, all the issues that may cause that affect flux or flow rate or absorption. All these things you'll need to know and you need to know the answers on all these before you can get into the ultimate cost modeling, which is really the only way you can somehow compare these technologies, unless you're running into a utility that has a specific issue that they have to address that really leads you one way or the other. For instance, the space issue for like ion exchange. Next slide, please. Now, some of these systems, for very small systems, for flow under 1 MGD, you can save money, even though the cost of treatment per gallon treated is higher. You can save monies on very small systems because you might not need to do certain things. Like you may have more residual handling flexibility, or you might be able to do a building that is pre-constructed building that you can put on place. You might save space. You might be able to save a lot of space between vessels, and you might be able to use smaller vessels. You largely don't have as much instrumentation for small systems. They oftentimes can be designed with no booster or backwash pumps. You can get away with smaller concrete pad thicknesses and reduced indirect costs. So there are savings for small systems. Next slide, please. And that's why on this, I'm sorry, keep going down until this is all done. I apologize. I wasn't looking at the other screen. And so that's what you see at 1 million gallons a day design flow rate, why there's this disconnect or discontinuity in the curves. You also drop down to lower costs. And this is an example of GAC treatment costs. It's for just one example. These costs will vary all over the map based on your example that you're trying to run. But here are the total annualized costs, which include capital and O&M costs per design flow rate. And you can work out the costing for these situations. In this case, 1.1 DCA is listed in red. And so it's nice to know that in this situation, the PFAS that we're looking at have lower costs than a compound that we know GAC has problems with. Next slide, please. And here's for ion exchange. And this is just, again, one example. In this case, you start seeing a higher cost for removal of PFHXA. And so the costing models can be very helpful for you in terms of deciding which ones to use. And one thing to note on this slide and the previous one is that at very, very small situations, say under 100 households, point of use RO could be a cost-effective option just because you're not dealing with treating all the water. Next slide, please. And here's an example of RO costs. So as a take-home, these models can be helpful to you. Next slide, please. Now, as I mentioned, that RO could have a concentrate stream that might be having to be handled, or other aspects in terms of things. We are looking at a whole bunch of other technologies, and this is a teaser for the next presentation a bit. And if you're adding in multiple technologies, the cost is going to get very high. But there might be some niche in some application where you can put together multiple technologies. Next slide, please. Here's a program that we're doing, or we're just starting at EPA, and it's a program for communities that want to identify sustainable and cost-effective treatment strategies for PFAS removal. And then the objectives are then to take the data and develop tools and approaches for them. And so our program is a technical assistance program funded to help the state revolving fund program for drinking water. And what we're doing with utilities, and we just started with a handful of them, and we're going to be expanding greatly over the next 5 years, is to look at extended periods of time, probably a year or two, conducting sampling and analysis of water systems for full-scale systems or pilot where appropriate, and help the communities optimize operation and maintenance issues. Oftentimes systems are put in and built, and then they're sampled for regulatory purposes, but it doesn't give you as much information as you could need for optimizing the operation and maintenance. And then we'll also work with the utilities on their residual stream handling. The goal for us is to develop enough data across the country to develop tools for performance and cost models, make sure the cost models are working correctly and performance models are working correctly, and then to link all that data and materials and tools so that people who have communities with similar water qualities and situations could use the information from our studies set of utilities into the future for the optimization of PFAS removal in terms of operation and maintenance. Next slide, please. We're looking for a wide range of water quality conditions, everything from concentrations of PFAS to background water quality. Some of the big things we're looking for communities is timing, where they're at with their treatment. If they got full scale in place, that's great. If they're just getting started, again, it's a 5-year program, and we can wait for them to get in place. But we do have a desire, we do have a need for the community to work, the desire to work with EPA and commit to a long-term project. This is something that we will handle all the costs for sampling. We'll make the coolers, the labels, the shipping, handle all that. But we do need the utility or community to be able to just take the samples when they get the cooler, take the samples, and then haul it out to FedEx and ship them back. And so this is and let's go to the next slide. And so, you know, the benefits are that the community gets a whole lot of data on optimizing their system and knowing their system, and then access to tools that are trained on the data from their system, and direct access to EPA technical experts that can help run models for them and go through all the issues that they have an interest in. They could also use the data, the final data for finished water. It's state dependent, but the states we've been working with are fine with, because it's done in a certified laboratory. They could use the data while we're working with them for regulatory purposes. And if they want to collaborate on publications, especially for those of the local community, EPA will be glad to work with them on those publications. Next slide, please, 31. Here's an example of a utility in Wisconsin we're working with. It's an emergency full-scale ion exchange treatment that they've dropped in place for a well, approximately 500,000 gallons a day. We're sampling bi-weekly. We're able to sample the system. We found the early breakthroughs of the early breakthrough contaminants. They were originally worried because they were going up and down and above the initial concentrations. But when we modeled it, it all fit perfectly. And then based on that, we've given them a real good feel for how long these emergency systems will last for them. And it's helping them with their final design for their system in terms of where they're going. The next slide, please. This is just a slide, and I'll go through this quickly because I want to hit the next talk, in that any system that can access the Drinking Water State Revolving Fund is available to this program if you're interested. Give me a call. Even tribally owned systems are eligible. They can use state revolving fund monies. Oftentimes they don't. because there are other funds available. But any system, even say schools and other very small systems that can utilize the state revolving fund can be part of this program. Next slide, please. And here's just a few places that we're starting. We're starting in Wisconsin and North Carolina and Ohio. We've got systems in Alaska and out in Guam and Northern Marianas Islands. Those systems we're doing a lot there, and the very remote systems we're working with the residual handling especially because they don't have the ability to ship back spent media, and so therefore we need to find and they also don't have natural gas for reactivation furnaces, so we're working with them on their residual handling needs. Finally, just to wrap up very quickly, the GAC ion exchange and high pressure membranes can remove PFAS. There are a lot of other issues. I could talk about this for a long, long time, and as you can see, I'm running even a little bit late here. But there are a lot of more issues to talk about, and I'd be glad to talk about it with anybody who has any issues. So the next slide is just a disclaimer and then questions, but we'll move to the next talk, which I can wrap up in 15 minutes. That shouldn't be a problem. So if we can
Hey,
go to the
Tom.
next slide. Yes?
Hey, Tom, it's Hannah here. While Sarah gets your presentation ready, we've only had one question in the chat, so I think I'm just going to go ahead and ask you now. And I'm also going to send it in our Google Meet so you can read it if you want to see it. But it's from Robert. He says, in my experience with GAC, we have seen coconut shell media have pesticide and herbicide concerns, and bituminous sourced GAC have metal issues. Can you comment on this?
Yeah, sure. So coconut shell carbons have largely been shown not to be that great for PFAS. I think the pore structure is such that at the end of the day, the more standard bituminous GACs and the standard ones, and are like the F400 from Calgon, have been basically borne out to be the most optimal for PFAS removal. That's pretty much everybody agrees to that. There can be some, minor nuances between one slightly different bituminous based on the other, but a bituminous-based carbon is the way to go. With regard to metal issues, I think you're referring to, like, say, arsenic issues. And GAC, bituminous-based carbons, can have, because it's a natural product, can have arsenic present in it. And we've known this ever since I started in the mid-80s. And it can be very easily handled with an initial flushing. In fact, a lot of manufacturers, if they know it's a concern, or will flush the carbon before they ship it. But sometimes, the memo gets lost, and sometimes it arrives on site and it's put on it's backwashed once, and then it's put immediately on in operation. And so definitely when you're working with the community, you'll want to go over the flushing procedure for arsenic with the GAC manufacturer. And I think recently, I know some of them have even gone to, like I mentioned, pre-flushing the carbon before they even ship it, just to alleviate that issue. So I think that's what is with regard to the metals issue. But if not, we can touch base at the end of the training. Okay, so here's the next talk. I'm going to jump right in. Next slide, please. This is the background slide, so we'll skip to the third slide. Yeah, here's a little bit of residual streams, and if it ends up going to the wastewater plant, it's just to note that the shorter chain PFAS or hydrophilic PFAS will end up in the treated water. The hydrophobic longer chain ones will end in solid residuals, which then find their ways to either incineration, land application, or landfill, and you can kind of start the cycle again if you're not very careful. Next slide, please. With regard to incineration, and this also includes like reactivation, you can send materials in, and you'll have other byproduct streams such as the ash, which we found PFAS in, incinerator ash, which is a little disconcerting, although the levels are much lower. but it can be there. And it also can be found in the scrubber waters. So there are the other areas of, of the cycle of PFAS that one would have to be concerned with. Landfills, we recently published a paper where we're estimating about 5% of the PFAS going to a landfill will go off as PFAS gas emissions, where about 10% end up leaving as leachate. So a landfill is not necessarily, a municipal waste landfill is not necessarily something that you can just walk away from. Next slide, please. Okay, so a little bit of some highlights that EPA is doing. I mentioned these Polanyi and the treatability database. On the disposal and destruction side, we have the paper, A Critical Review of PFAS Landfill Disposal, which I mentioned the results from on the previous slide. And we do have a PFAS thermal treatability database if you're interested in that. And we've done some projects with pilot scale destruction of PFAS of AFFF. Next slide, please. This is just a little bit about thermal destruction technologies, and I'll be concentrating largely on incineration and reactivation. So next slide, please. And those are covered in the thermal treatability database. So if you jump on this, it's pfast.epa.gov. If you get to the database, you'll be able to see the reference information on the treatment of PFAS in thermal processes. We don't include like SQO and HALT and things like that, but largely the processes that specifically use heat to destroy the PFAS. Next slide, please. And why that's important is that PFAS, the carbon-fluorine bonds, are particularly strong, and that the most difficult one to destroy is carbon tetrafluoride, which requires like 1400 degrees C to achieve 4 logs of destruction. And that, and along with C2F6, can be used as potential surrogates in a thermal system. You know, the numbers right now for PFAS, the regulated PFAS, we're looking at numbers somewhere around 1100 degrees C for a good percent reduction without PICs. And that's the key here, is that we don't have a lot of field data, and that field data is lacking a lot of information on products of incomplete combustion. We know a lot from bench scale, but how that scales up is we don't have a lot of data in that area. And also we have struggled over the last few years, and we're getting better and better at it, because the gas phase sampling and analytical methods are still being developed. They're behind the water methods. And so keeping track of the volatile, non-volatile, polar, non-polar constituents has been a challenge. Next slide, please. In terms of destroying the resin, oftentimes cement kilns are recommended. They're very high temperatures and also have high residence times in terms of solid residence times. And so therefore, that is one aspect that the manufacturers oftentimes recommend. We have not studied it. If you know of a system, like cement kiln, that's willing to load in PFAS-loaded resin and have EPA sample it, let me know. But that is one option in terms of getting rid of the resin, as is landfilling. Next slide, please. Here is a little bit on GAC reactivation. We've done a lot on this. We've done a lot of bench scale work on GAC reactivation. We've done pilot studies on GAC reactivation. Those results are just coming out in the next month or so. And we've completed a full-scale study this summer, and we're still waiting on some of the analytical results to come in. The bandwidth on some of the sampling and analysis can be lengthy, as some of you know. And although we are working a lot on this, we are still looking for partners if you're interested. As an FYI, Calgon Carbon published last year on reactivation of GAC, largely for the known GACs, known PFAS And if you're interested, it's that Stefano reference. Okay, a little bit now, next slide, please. A little bit now more about managing PFAS. And this is a paper that was done in last year, and I'd recommend it. Next slide, please. The flow rates of membrane concentrates are fairly high, 20 to 30% of the feed. It can have high PFAS and salt and background levels and concentrations of other contaminants. So it's a little bit of a tricky wicket in terms of treating. Next slide, please. And in that publication that I referenced this is the technology residence level kind of approach looking at it. So on the x-axis, is it ready to be utilized? On the y-axis going up is can it manage PFAS in RO concentrates? And what you see is that, and I'll go through the different categories one by one. So next slide, please. We know that concentrating PFAS with adsorption, reverse osmosis membranes, or more unique membranes, membrane distillation, or forward osmosis, and those kind of skew along the range of whether or not it's ready or not. But it can reduce this issue of concentrate treatment. And you can get into brine concentrators and crystallization, heading towards zero liquid discharge. And also, as you go down the list, for things that aren't quite ready yet, is electrocoagulation and coagulant-aids. But if you're looking for treating the RO concentrate, the first one on the list is either using other membranes to concentrate it even further to the point where you can manage it, or use adsorption of one type or another. The advantage is you don't necessarily have to use, you can use a more novel adsorbent that maybe isn't NSF certified for drinking water for this capability. Next slide, please. For treating other type of concentrating factors, the other blue ones, you get into evaporation ponds, foam fractionation, which is moving forward fairly quickly now. The question with foam fractionation is at what concentrations is it really effective in the system, and more data is being generated on that. And then you have other things, and I mentioned this before. I mentioned it skews with some of the other membrane systems for membrane distillation and forward osmosis. They're not quite ready for prime time, so they're further there on the left. And on the very low bottom end is like electrodialysis and RO hybrid systems. So it's quite, that has a lot more to go before one would consider that. Next slide, please. This is just a foam fractionation for those that don't know. You bubble air through your water in one way or another by pulling a vacuum or pushing air through it. And it's a lot like air stripping. And PFAS love to be at the interface of the air to water. And so when they get to the top, it foams up in a sudsy foam, and you can kind of scrape it off or suck it off. And that can be very effective, especially for long chain PFAS, and could be used as an RO concentrate treatment, or if you have an extremely high concentration in your well, you might be able to use it as a pre-treatment to your primary treatment system. And that's probably more for cleaning up hazardous sites as opposed to drinking water systems, because the concentrations do need to be high. Here are the defluorinating PFAS technologies. So incineration, plasma-based treatment, sonochemical, electron beam, supercritical water oxidation. Incineration is possible, but you can't incinerate 30% or 20% of your feed flow rate. So you're going to have to knock it down for that. And the other technologies aren't just quite ready for prime time. But it can be helpful, but none of these technologies are 100%, not even electron beam where you're just zapping it with electrons. Next slide, please. And here's the slide on electron beam. So it's a radiation method that's been used for decades in the food industry. You can really send a ton of power into your water, but at the same time, it's not going to be 100% effective for PFAS. Next slide, please. Supercritical water oxidation is something that's very promising. We don't know about it in terms of an RO concentrate stream. That's a continuous stream. But for batch type streams or very low flow rates, it could be possible. We piloted it in a number of different situations, and we're going to be running one shortly, looking at sewage sludge actually. But it's a promising technology, but not necessarily for RO concentrates. Next slide, please. Other potential destruction technologies: zero valent iron, sonochemical, advanced oxidation, UV irradiation, hydrated electrons. They're all not quite ready for prime time. Biological treatment, they've shown a bug or two can eat certain PFAS to a certain point, but it's very unique bug, and it would require like iron and ammonia being present, and it's not ready for prime time. So if you hear it is, don't necessarily believe it. Next slide, please. Electrochemical oxidation. This is another technology, as you can see by the picture. It's just being worked on largely at the bench scale. There are some piloting systems out there, but we've tested it. It seems to work well for certain PFAS. There are always breakthrough products on that. And so that's another technology that's being studied. Next slide, please. Okay, so deep well injection, that's been used for RO concentrates, not necessarily for PFAS. I think there's been a couple cases of putting a PFAS stream from landfill leachate into deep well injection, but not necessarily for RO concentrates, although it's been used for that. So it could be a possibility in certain locations. It's very expensive. Landfilling, you'd really have to knock down the volume before you send it to a landfill. And so you'd have to use some other technology also, most certainly. Next slide, please. And this is just another slide of when you start adding in all these technologies, it's just a note that it's going to be very expensive. Next slide, please. And here, this is the same slide on our system, and I just want to reiterate that we are interested on this community program to work with communities on managing their residual waste streams. And we're very much open to looking at situations like that. So I'd like to just now acknowledge the next two slides as my TPA co-authors, and then the co-authors on that paper that I referenced. And then it just ends up with a disclaimer and the questions. So I apologize for kind of going through this. As you can tell, I could probably talk about this topic for all day long. And I hope it's been valuable to you. And I know there'll be a time at the end of the whole thing that we could answer more questions, and I look forward to that.
Thank you, Tom. We do have one question that's come in, and since we are just a couple minutes late, why don't we go ahead and do that one now? Hannah, would you be able to read that one, please?
Yes. Hi, Tom. We have one more question, and the question is, when GAC is used for PFAS removal, is there any data to show what happens to PFAS during GAC reactivation process? Is it completely removed during reactivation? And I'll go ahead and share this in the chat so you can read the question as well.
Yeah. So we've looked at that a fair bit. So on the bench scale work, we funded a couple of universities to do this work, and are continuing it. At the bench scale, it shows largely all defluorination to hydrofluoric acid. But at the bench scale, it's very controlled. It's a very controlled system, and you can kind of get those results. But the good news is that it appears very clearly that activated carbon, when you heat it up to reactivation temperatures, which are below 1100, the functional groups on the activated carbon work as kind of a catalyst to help destroy PFAS. Also, if you can catch it quickly, heat it quickly, the carbon can hold the PFAS within its pores for long enough time, it seems, to destroy the PFAS before it being released into the gas phase and then quickly exiting the system. So that's the advantage of heating using reactivation for destroying PFAS, as opposed to another incinerator that might immediately go to the gas phase or not have these kind of catalytic properties. Now, it changes when you get to full-scale systems, just because full-scale systems aren't quite as efficient and have some peculiarities in terms of flow rate, flow dynamics on the larger systems. and that's where we don't have a lot of data. The Calgon data suggests that it's very effective for destroying many PFAS. There were some things they found coming out out of the top of the reactivation furnace, and that was with a carbon that was very heavily loaded with PFAS. So it looks promising. We don't know anything about the products of incomplete combustion, of whether or not it won't go to 100% hydrofluoric acid because of the fluoride flow concerns. But it looks very promising. We just don't have a lot of data in that regard. We have finished a pilot study, and this summer we ran a study with a reactivation system that was treating drinking carbon that absorbed PFAS in a drinking water application. So more typical of drinking water loadings onto carbon, and we're hoping to get that data out soon. So the short answer, that was the long answer. The short answer is it's promising to destroy the PFAS onto carbon, but we're waiting for the final numbers.
Great. Thank you, Tom. That was really informative. We really appreciate your time this morning. Now we're going to switch to Dr. Yasmina Markovsky. She is a senior engineer with the Safe Drinking Water section at ADEQ. She holds a bachelor's degree, a master's degree, and a PhD in chemical, polymer, and environmental engineering with a PE in chemical engineering from the state of Arizona. She has 11 years of experience in the industry and is specialized in adsorption and ion exchange drinking water treatment technologies. She's the author of 4 patents, 22 peer-reviewed publications, 4 book chapters, and more than 30 conference proceedings and presentations. So with that, I'm going to change presenter to you, Yasmina, and we'll get your presentation started. All right. All right, Yasmina, are you there? I don't hear you. Yasmina, are you having any issues? Are you muted, Yasmina? I'm still not hearing you, Yasmina. Okay, looks like Yasmina is gonna come in again. She is our speaker for the next 2 hours, so let's just give her a minute to see if she can get back on. If not, we may take our break a little early and troubleshoot here. Oh, I hear
Hello,
Yasmina.
can you hear me
Okay,
now?
yes, there you are. I've given you the screen. Okay. We wait for Yasmina to come again. We do have a question that we can work with here. The question is for Tom. GAC is the most widely used technology for PFAS. It's cost effective and efficient when designed well. However, not all utilities employ GAC treatment. I was wondering why this could be the case. Is it because they're not mandated to, Also, according to you, how many people do you think receive GAC treated water in the US, just as an estimate?
Wow. Okay. I'll try to. You might have to remind me what they are again. But so yes, GAC is used fairly often. It's really difficult to tell because I'll start with the last one first. Is that it's difficult to tell what percentage of utilities use GAC. I'm getting a little feedback here, but hopefully it's not too bad. Because some utilities use GAC for taste and odor, and other utilities use it for removing, synthetic organic contaminants or some contaminant. So in that regard, it's hard to kind of match up with what you're doing. With regard to using it to remove specific contaminants, oh, and then some utilities use it to remove disinfection byproduct precursors and to be just a kind of a barrier against other contaminants that might be coming down a river, for instance. So I would say that I don't have the hard numbers on this. I used to know 20 years ago. It's something along the lines of, for taste and odor issues, like maybe like 10% of the surface waters or something along those lines. There's only probably not a huge number of utilities that use it for SOs or for contaminant removal, but there definitely are some. So I could get the numbers for you if you're interested. But it's not a hugely used process, although it's been used for decades, and it is known as a very drinking water friendly.
Okay.
Drinking water friendly. There's a lot of static there, but with regard to GAC being used, why would somebody not use GAC? Perhaps the water quality, say there's a high TOC concentration in your water. Sometimes that has been shown to be more effective to go to ion exchange as opposed to GAC. So that could be one reason. Another reason, as I mentioned in my talk, is that maybe the utility is landlocked and doesn't have a lot of space, and the ion exchange columns are much smaller, and they can fit within the utility, and they don't have the option to go with the larger columns. I've even seen it where the building is shorter, and they couldn't get in the standard GAC column because it's taller than the ion exchange column. You couldn't get it in through the door, so they went with ion exchange. So it could be a footprint kind of issue. It could be a water quality issue, and you really need to kind of do some piloting or some sort of testing to choose your media selection. So I think I answered the 3 questions. I'm not sure.
Okay. Thank you, Tom. Are you guys able to hear me okay? And Yasmina, would you read your bio if we can hear you?
Hi, can you hear me?
Yes, thank you. Thank you. All
Oh,
right.
good. Yeah.
I will introduce you and then we'll turn it over to you. So Dr. Yasmina Markovsky. She's a senior engineer with the Safe Drinking Water section of ADEQ. She holds a BS, MS, and PhD in environmental engineering and a PE in chemical engineering. She has 11 years of experience in the industry and has specialized in adsorption and ion exchange drinking water treatment technologies. And she's the author of 4 patents, 22 peer-reviewed publications, 4 book chapters, and more than 30 conference proceedings and presentations. Okay, Yasmina, we see your presentation. Take it away.
Sounds good. Thank you. Let's see how does it look in a full screen mode. Okay. Is it still good?
Yes, looks good.
Okay. Well, let me get started. Sarah, thank you for a great introduction and good morning, everybody. In today's training, I will talk about permitting considerations specific for PFAS treatment projects. And thanks to Tom's presentation, my job should not be difficult this morning. But before I start, I will read a full disclaimer saying that the views expressed in this presentation are those of the individual authors and do not necessarily reflect the views and policies of the ADQ. mention of trade names or commercial products does not constitute endorsement or a recommendation for their use. So over the next 2 hours that we have for this training, I will be talking about general goals and objectives when it comes to PFAS treatment design and permitting. I will define 6 steps in permitting process. And before you raise a red flag here, I have to say that nothing is changed in terms of ATC and AOC, but I'm going to talk about all the other steps that you are doing prior to submitting ATC application or in between ATC and AOC. So here we have water quality parameters, analysis, design considerations, testing, ATC, startup, and AOC. After that, I will show you an example of successful PFAS treatment that is operating for the last 2 years in Arizona. Then I will explain where we are at the moment with point of use and point of entry units in terms of compliance acceptance options, and summarize ADQ work in progress that will soon provide additional support for PFAS projects. And at the end, depending on time, I should be able to do short demo with pore surface diffusion model. So let's get started with goals and objectives. I found important to step back here and say that before start thinking about treatment at all, be aware that treatment is not always the best approach. Non-treatment alternatives such as consolidation, interconnection, or deeper wells may be better option. And here are some reasons for that. So these non-treatment alternatives can be faster, more cost-effective, and more sustainable. You will not have a long-term O&M consideration here to think about, or no limitations for technical, managerial, or financial capability, as in case of treatment. For purpose of this training, I will assume that non-treatment alternatives are already explored, but for some reasons not working for you, and you are starting to think about treatment options. From ADQ point of view, high level of PFAS treatment goals are long-term compliance and simultaneous compliance. We understand that there are both positive and negative specifics related to PFAS. So while we have known treatment technologies and grants are available to support robust design, certain gaps do exist. So this is still new contaminant for us. We are dealing with very low concentration, so we are basically targeting non-detect. And there is a general lack of experience in all the fields related to PFAS. So in order to meet goals in line with these listed specifics, we see 3 main treatment objectives. First, design must be reliable. Second, in-depth planning and testing is needed. And third, selection should be driven by system specifics. So this slide provides more information about non-treatment technologies and demonstrates that there is no strict line between not effective, and developing ones. So if you look at this graph from 2018 publication, you will see that at least 2 variables should be analyzed when exploring treatment options. So even with all the technology development, 5 years later in 2023, we are almost at the same place, and based on a range of practicability and stage of development, activated carbon and ion exchange are still best available technologies, which is why we recommend them with no really intention to limit your selection or proposal for other technologies. After all, treatment selection shall be driven by system specifics so that final product is reliable and easy to operate, and it should avoid and prevent foreseeable mistakes. And of course, it should be cost effective. But when we say cost effective, it's not only about the capital cost, but you also have to think about balanced capital and long-term O&M costs. So in Arizona, we have very small rural systems, such as the one on the left side, but also big ones shown on the right. While they may have same PFAS issues, their optimal treatment selection and design will not be the same because of their specifics. I will now start with permitting process. And even though this process is nothing different than what we have for any other treatment and contaminants, I will show here a recommended cadence of activities needed to, to meet minimum design criteria with emphasizing differences specific to PFAS. So you're all familiar with ATC and AOC steps in ADQ permitting process. However, there are activities that you do before and in between ATC or AOC. So, and I will talk about all of them. So our goal is that you come prepared for ATC or AOC so that you do not risk denial. And that's why, in addition to these general type trainings, we highly recommend scheduling pre-application meeting with us where we can answer all of your questions and determine if your specific project is ready for ATC or AOC submission. So first activity on previous chart is analysis of water quality parameters. This should not be surprising for anyone because you have to know what you have in your water in order to plan how to mitigate that. Questions that I thought that may arise specifically for PFAS as a new contaminants are what to test, where to test, and how many tests to do. And you have to know answers on these in order to provide crucial information for your design, such as what PFAS you have, what compounds, in what concentration, and what is the variation in them. Then beyond the PFAS, you have to know the same for competing and fouling background water quality parameters. But even beyond those two groups, there are other potential water quality interferences that you have to test for. So let's focus on PFAS only. There are three things that you have to know about PFAS in your water. First, you have to know speciation. And why is this important? It is important because you have to make a difference between short chains and long chains, because longer the chain, stronger the hydrophobicity and lower the mobility. So that's why you can see that it is easier to remove, general trend saying that it's easier to remove longer chains than shorter chains. Then you have to know what's the functional group that you have in your PFAS, because stronger the head charge, it's easier to make the bonds with media. And you can, I guess I can give here one example. So you probably already know that it's much easier to remove PFAS in comparison to PFOA. So there is only that functional group that makes difference here. So it's very important to know which one you are dealing with, what you are targeting. And then you have to think about the potential for future regulations. And you are screening for 29 compounds, either if you are looking at that those screening results from UCMR5 or ADQ testing, you are testing for 29, and we have 6 of them that are proposed for regulation. So I really recommend to observe all of them. So, you know, you should not be focused on 6, because if you are testing from 29 and you see that something else, some other PFAS compound is issued, then consider to treat that as well. So after you know your speciation, think about concentrations, because concentration is driving factor for design, because it is driving that breakthrough curve and, you know, controlling media lifetime. And then you have to know about the temporal variations of both concentrations, or maybe also speciations. So that's why you have to design for worst case scenario, and for that you need more than one sample. I guess we can say here, plan for worst and, you know, hope for best in this case. So how to get this information? Well, start with existing data. Review what you have from UCMR5 or ADQ sampling, and you will already have idea what you are dealing with. For number of sampling events, well, it will really depend on the source and the site specifics. And I would say that the minimum that you have to do and have data for is what we have with the UCMR5, and we'll talk about more. For sampling location, well, again, we have this screening sampling that is going on EPDSs, but that's not enough for design. So you definitely have to go back, and beyond EPDS, you have to know what is in your raw source water. And here, this table is showing sampling frequency for UCMR5 that I mentioned. So here you can see that there is a difference between surface and groundwater source, and the reason for that is that different variability expectations. So for surface water, you have 4 sampling in a year, while for groundwater, it's only 2. But please note that the number of months apart is very important to catch impact of seasons, and lower the number of sample is, the most important this time step becomes. Okay, this seems to be a mistake. This slide was not supposed to be here. Okay. So there are other things in your water beyond PFAS that should be analyzed due to potential negative impact. So we have 2 major groups of interferences here. One is competing, and the other one is fouling parameters. Competing is important because it affects capacity for PFAS, because if you have many contaminants competing for same sites, and, you know, absorption sites are limited. So it's very important to know what is competing and how much of that you have, because it's only limited number of sites that you have available. And that's why that can drive trade-off decisions. And then for fouling, fouling is important because fouling is basically clogging your pores. And if you clog those pores, you are basically blocking those absorption sites. So by clogging pores, you are affecting media capacity as well. And you also increase that O&M activities and eventually cost. And fouling can require treatment to avoid frequent backwashing. In general, competing parameters are more important than fouling because they cannot be removed with one pre-treatment vessel, and usually require more complex treatment trains. And as with other water quality parameters, you have to do tests in order to analyze impact and plan mitigation here. So to help with this effort, ADQ provided lists specifying water quality parameters that are of PFAS treatment interest. Please note that this list is minimum that should be tested, and the other parameters may be needed as well. So to demonstrate importance of testing water quality parameters in PFAS treatment, I summarized here some trends that were presented recently in EPA workshop. Let's first go over GAC. So it was found that initial concentration and coexisting PFAS have little influence on PFAS removal capacity. So here they tested a range between 60 and 5,000 ppt. Then it was found that TOC has a very strong negative impact on PFAS removal capacity. And that's what Tom mentioned a few times. So in this case, they tested groundwater that had less than 0.3 ppm TOC, and some surface water up to 4.7 ppm of TOC. They also found that nitrate had a negative impact on GAC, but not that dramatic as TOC. On the other side, ionic strength had a positive impact, and this is not still well understood, but it's potentially because electrochemical double layer theory. And then on the other side, for ion exchange, situation is a little bit different. So here, PFAS structure has the greatest impact on PFAS removal capacity. And that's probably because ion exchange is more selective media, and that's why we see that impact as more strong. Similar to GAC, also with ion exchange, we have negative impact of TOC and nitrate. However, it's interesting here that TOC impact affected more long chain PFAS compounds, while nitrate impact was more strong on short chain PFAS compounds. So altogether, based on what is published so far, I would say that list of interferences is not surprising because it's dictated by PFAS and media properties. But the difference that I see is that the impact of background parameters is stronger than what we are used to see when dealing with other contaminants, other common contaminants. Which is probably driven by low affinity of PFAS for adsorption and a low concentration gradient, because we are in PPT range with the PFAS, which is sometimes 6 order of magnitude lower in comparison to other interferences. And here are some screenshots from that work just for better demonstration. So this graph is showing how the different TOC concentration affected GAC breakthrough curve for different PFAS compounds. I put red arrow on PFAS, on PFOS, just as an example. And you can see that basically any TOC is dramatically shortening a GAC lifetime for PFOS. So if you have groundwater with, let's say, non-detect TOC, you can do more than 150 bed volumes before reaching 10% breakthrough. But even slight increase in TOC, and here that was to 1.3 ppm, results in bed volume drop to about 15, 20, which is 10 times reduction in media lifetime. So while it's inevitable that this impact will be extremely important if you are dealing with surface water, it is also warning that even small increase in TOC may significantly change your media performance, and that can even happen with groundwater. And here in this slide, it's same work just for ion exchange. So if you look at the graph on the left side and compare media performance for TOC of 0.7 to 1.2 and 2.2 ppm, you will see that media lifetime can go from about 200,000 bed volumes to about 50,000 bed volumes, or cause 4 times more media changeouts. Another graph on the right is showing nitrate impact. And nitrate is important because same type of resin removes both PFAS and nitrate, and therefore they compete. So here we have data for nitrate, and you can see how they're shifting left, this breakthrough curve left, when you are going from 0.5 over 93 to 186 ppm. So this basically means that if you have nitrate about 2 times MCL, which is shown with this middle line, so don't be confused here. These results are NO3, and if you express that as nitrogen, it will be about 21 ppm. But if you have just twice MCL in your water, your ion exchange lifetime will drop at least twice if you want to use same treatment for PFAS. So someone may say, well, I will just regenerate more often. And unfortunately, this is not a recommended option here because regeneration of resin with PFAS is different. It requires organic solvents, and eventually management of PFAS-rich waste is more complex. And as I said earlier, to help with this effort, ADQ provided lists specifying water quality parameters that are of PFAS treatment interest. Please note that this list is minimum that should be tested, and other parameters specific for your project may be needed. A list includes PFAS speciation, cations, and anions, and other water quality parameters that you may have impact on treatment performance. And now we are going on second permitting step from flow diagram that I showed, and this one is called design considerations. So this topic is broader than first one, and its purpose in general can be covered by 3 questions that this step should provide answers to. So first, how to design for specific outcomes. Then what to consider as potential system limitations, and how to get rough cost estimates. So at the very least, these answers should be based on a system-specific analysis that includes following items. So existing conditions, operation, residual management, applications, implications, and cost estimates. And I will talk about all of them in next slides. So here is a list of some common items that should be considered when analyzing existing system conditions. So it is important to know source water type. Then what is the typical operation of this system? What's the frequency and percentage utilization? What's available pressure and how does it vary with all the treatment elements? Then what is there any existent treatment? And if yes, what's the treatment practice? Also, are there any existing problems? Does this system has issue with sending bacti? And eventually, how is all of this like managed, mitigated? Then what is proposed location to add this PFAS treatment? This is very important because you have to know what is upstream, and especially what chemicals are used upstream of this proposed location. And then what is ability and what are the restrictions on disposal of flush water or, let's say, emergency chlorination. So this is just a general list to give you idea what to think about, but another important thing that I would like to emphasize here is that operators' involvement is critical at this step. So they're the one who run existing systems and they can identify issues the best. So they're also users of your future design, and as such, they should be involved in early stage of the process, ideally here. Next step in design considerations is operation. So because of its complexity, I will be focusing only on few aspects, where first one is selectivity and kinetics. So this table and many others that you will see through this presentation are comparing 3 best available technologies. For the sake of time and not high practicability or expected interest for membrane processes in Arizona, I will talk more about GAC and ion exchange. And due to different mechanism characteristics and selectivity and kinetics, actually due to this mechanism characteristic as a background, both selectivity and kinetics of these 2 technologies may simply rule out other option. So in terms of selectivity, GAC is not very selective technology, and we mentioned that many times so far. And as such is less effective for shorter PFAS chains. While ion exchange is synthetic material with specifically designed functional groups, and that's why it is effective for wide range of PFAS. Well, this means that PFAS speciation may really drive treatment selection. On the other side, kinetics of GAC and ion exchange is also very different. And due to specific empty bed contact time needed, footprint for equipment may be 5 times up or down, and space limitation may easily dictate your treatment selection. Finally, it is important to recognize that GAC and ion exchange media beds are very different, and comparison should not be based on bed volume treated, but on water volume treated. So another aspect of operation is to know more about pressure vessels, requirement for both GAC and ion exchange treatment. I say pressure vessels because gravity GAC basins are not recommended for PFAS removal due to issues that we'll cover in following slides. Again, here is a checklist created to help you with your analysis and planning. So vessels should be NSF 61 certified. Tank sizing should be based on empty bed contact time and hydraulic loading rate. Your vessels have to provide even flow distribution, and then they're pressure vessels, so there has to be some way of pressure relief valve or rupture disc to control that potential excess pressure. Then you have to know where you are in terms of media lifetime. So you have to have a way to measure your flow. So it is very good to have a flow meter per your treatment train. Then you have to have a pressure gauges because you have to be able to monitor that pressure drop. So pressure gauges should be on more than one site in your vessels. Then you have to have a flow control, and then piping and valving to support flashing. Then you have to be able to switch vessel positions in treatment train. And then you have to know what is going on with your mass transfer zone. So sampling ports are also very needed, very important. So you have to have them on few locations. then media trap, and compliance sampling port. And eventually, because we are talking here and really recommending lead lag configuration, you have to have a way to clearly label what is lead, what is lag. So here we are recommending magnetic lead and lag labels to help operators with the position. So going further with operation, it is important to understand vessels configuration. So you already saw some of this in Tom's slide, but let me just repeat some things. So there are a few options here. First, as shown on the left side of the slide, you have to think about number of treatment trains. And here you have a trade-off between cost and redundancy. So in order to be able to alternate usage of these treatment trains, you have to have multiple trains. And that's actually the only way to secure that continuous operation. Second, regardless of treatment train number, you have options for parallel or lead lag operation. So this decision is a trade-off between complexity and efficiency, and I would say also safety, because lead lag system will increase media efficiency, and it also is going to provide increased margin of safety. And in line with that, it will help you with managing chromatographic peaking that is very significant for PFAS. And I'm again going to talk more about that in next few slides. So the last aspect of operation that I have here is pre-treatment. It is well known that for any type of contaminant, pre-treatment addition will maximize treatment capacity and reduce general issues. So this impact is, however, even more important here when dealing with PFAS, because what we really want here is to minimize or eliminate need for backwashing, and that way prevent disturbance of mass transfer zone. So this means that even if your source has no specific issues, bag or cartridge filters is recommended ahead of ion exchange or GAC, and in that way you will minimize dirt and particles accumulation on the top of media bed. So otherwise, for specific issues, you should select specific pre-treatment. So for example, if you have sanding problem, you will have sand separator. If you have issue with iron and manganese, you will put as a pre-treatment filtration with oxidation. Then you may have a free chlorine in your water, and that means that you will have to do dechlorination before ion exchange treatment because you want to prevent that degradation. Again, if you have very hard water, you may have to do softening ahead of ion exchange treatment. And if you have organics, maybe you want to consider to have hybrid approach and, let's say, combined GAC and ion exchange vessel. So have a GAC as a pre-treatment here for ion exchange, or have lead lag where lead is GAC and lag is ion exchange. So just to add here that disturbance of mass transfer zone is one of the reasons why the gravity basins that have frequent and intensive backwashing are not recommended for PFAS. So we are done with the operation and going now on another item under design consideration, which is residual management. So there are 5 categories of residue that you potentially have to design for. These categories are spent media. So if you have GAC on ion exchange, that spent media will contain PFAS. Then the second category is concentrate reject water stream, and we are talking here about your waste from reverse osmosis or nanofiltration, and those concentrate stream will have very high concentration of PFAS, of course. Then third category of residue might be your initial flush water. So basically, if you get a media that was not flushed by the vendor, you have to do that on site. So if you have ion exchange in that flush water, you may expect to have some VOCs there. If you have GAC, it will probably be some arsenic in that initial flush water. So you have to have a way to manage that. And then fourth category is backflush water. And we do not expect to see here any PFAS because just backwashing should not be strong enough to do desorption. So there should not be PFAS, but yes, you will have fine particles. And then if you have pre-filters, that will be additional residue category. So you will have to wash those pre-filters, and again, because they are not effective for PFAS, there will not be PFAS accumulated, but some other things will be there. So you will notice here that in red are residual categories that will contain PFAS, and that is what makes difference here in regards to other projects that deal with arsenic or nitrate, for example. So difference is that there is a pending proposal for PFAS waste hazardous designation. I listed here timeline for this proposal, and information that we have at the moment is that February 2024 is estimated time for final rule. But nevertheless, even before official regulation, for the sake of generator liability, we recommend that that your design should plan for this rule. And this table is comparing residual management options depending on treatment technology. Again, Tom mentioned most of this before, but media reactivation is possible only for GAC. If not reactivated, media can be disposed on landfill or incinerated, where all three options require specific special conditions and probably hazardous approach due to properties of PFAS. Residual water streams should not be concerned for GAC and ion exchange because they will be generated only in case of media flushing that ideally should be minimized or avoided with help of pretreatment. On the other side, this residual water stream is huge concern for reverse osmosis systems due to constant generation, high volume, and potential hazardous requirement, because here obviously dilution is not solution. So here is a short summary focusing only on PFAS spent media. Basically, every basis of design for any PFAS project shall analyze quantity of waste, logistic, and cost associated with that. There are only two existing options for PFAS media residual management, and those are landfilling and thermal destruction, where we have reactivation and incineration. Unfortunately, there are issues associated with each of them. So for landfilling, we have that proposed hazardous designation, and we don't have any hazardous waste facility in Arizona. I think that the closest one is in Nevada. Then we have general lack of data. So we don't know too much about destruction pathways, and then we are missing that field data that Tom mentioned, and we also need to know more about emissions. If you think about thermal destruction, only specialized facilities can do that because of that high temperature requirements. We have a Calgon Carbon facility in Arizona, and we are going to work with them in the future to get more information about this. But you should also know that this approach might have some limitations in the future. And this slide is demonstration of issues that some sites are already experiencing. So here specifically, we have Guam Island that have a GAC treatment for PFAS, but not a solution for spent media because they're so isolated. And as of now, spent media is sitting in bags and waiting for disposal resolution, while Guam is looking for treatment improvement in order to prolong GAC media lifetime and eventually generate less GAC waste in the future. So look at this as lessons learned, and in line with previous slides, really provide design that will prevent these types of issues. So we are going on next topic now, and that is also under design consideration. So we are going to talk about application or utilization of same treatment for PFAS, but also for other co-contaminants. So instead of saying yes or no for this approach, let's start with treatment overview. So we have GAC as the most practiced technology in US. Ion exchange, something less, and finally reverse osmosis that is very rare in non-coastal states such as Arizona. GAC is more common in big systems with surface water source, where its goal is really TOC reduction, while ion exchange resins can be seen in small systems on groundwater that have issues such as nitrate, fluoride, and arsenic. So in regards to PFAS, it can be expected that big system can still use GAC if they have to remove a long chain PFAS compounds. However, due to high TOC competing impact that we mentioned before, it is likely that additional GAC vessels will be needed at the end of treatment trains to address PFAS specifically. And similar is with ion exchange. So while small system footprint and short chains can dictate ion exchange application, PFAS will likely require additional ion exchange vessels because regeneration is usually not recommended for PFAS, while it's crucial for ppm contaminants. And after application, another thing to consider is implications or simultaneous compliance. So there are at least 3 potential impacts that installation of PFAS treatment can cause. First, for corrosion control, installation of reverse osmosis will have extremely significant impact and will require some mitigation measures. Ion exchange will change anion ratio and cause pH drop, but luckily this impact seems not to be long-lasting according to recent publications. On the other side, GAC will probably be beneficial for corrosion. Then second thing to think about is microorganism colonization. This can happen with any granular media or membrane technology and must be managed, which is usually done by addition of post-disinfection. Third, chromatographic peaking, that is also called dumping, is generally associated with granular media technology. This phenomenon is, however, significant for PFAS, and it will start to leak out as a result of co-contaminant push impact. Let me show you more details about that. So here is a visual explanation of chromatographic peaking effect. So this effect is a result of two factors that drive adsorption. First one, affinity, and the second one, concentration gradient. And the issue here is that neither one of them favors PFAS. So someone recently asked me if this is similar to bully effect, and I realized that that was a great comparison, and that's how I ended up with this schematic. So when this bully thing happens, the concentration of PFAS in effluent will exceed concentration in influent, and this may be very significant. You can see 2 times higher concentration. And really common way to mitigate this is to have a lead leg configuration. So you have that extra safety factor and you are able to catch that. And also you have to have extensive non-compliance monitoring that will cover also like that middle point between the vessels, but also multiple sampling ports. And last aspect of design consideration is cost estimate. So cost estimates then in early phase of design are part of conceptual design. And purpose of doing one is to really narrow treatment and design options and check for TMF capability of the system. So even though this can be done in many ways, I assume that each firm has preferred way of doing that. ADQ recommends use of cost model prepared by EPA that are free of charge and have options for non-treatment, but also for all 3 treatment technologies recommended for PFAS. At the moment, we are working on updating this model so that they use Arizona-specific cost for 2023, and also have also are specific for made in US materials. And also, we would like to see update with displaying more details in the output tables. However, this is work in progress at the moment. And I can say here that if you use these EPA models, you will significantly simplify comparison between mitigation options and have easier and more straightforward communication with ADQ. And just few notes here. So when using this model and putting information for residual, it is recommendation to plan for this proposed circular designation. And then for reverse osmosis, I mean, if there is no specific reason and you know that you are not going to use that, you don't have to show us that, you know, this is not like cost effective for your system. But again, if you are considering reverse osmosis, the focus definitely shall be on reject water management. And here are some screenshots from EPA cost models for non-treatment options. First screen is input one, where you can select interconnection or new well construction. And second screen is output summary showing total costs with details provided in supporting tables that allow further modifications. Calculator for treatment is similar, but you have to put here more input information. And what is very important is that you may select between a non-hazardous and hazardous option when planning for residual disposal. And here is the moment when we plan to have a break. So Sarah, can we check a time and see if this is doable?
Hi there. Yeah, so we'll be taking a break and we'll get back at 10:15 and begin again. So it's just about 10 minutes. So yeah, we'll see you back at 10:15.
Thank you. Hello.
All right.
Hannah.
Oh, sorry. Yep, it's 10:15, so we're going to go ahead and start back up with the presentation. Yasmina, please take it away.
Sounds good. Can you just confirm if my audio is okay?
It sounds clear and great to me, so I think you're good to go.
Okay. Here we were. Give me a second now. Okay, so I think that for the rest of presentation, we have 30-something slides, but we are now on step 3, or testing. So it is great that there are more than one type of testing or model prediction that you can do in order to provide information about media lifetime, scale up details, and more detailed cost analysis. So while having many options is great, sometimes it can be very confusing. So that's why today I'm going to talk about each of 5 listed options, with the goal of explaining what tests should be selected for what results and how these tests should be combined. So this slide shows recommended step-by-step testing approach, or you can call it roadmap, for optimal design determination. It is interesting to note here that this roadmap is not PFAS specific and should be followed for any testing for any contaminant. But unfortunately, it seems that the more we know about some contaminant, the more is skipped from this list. However, now we are dealing with something new, and following this roadmap is highly recommended. Roadmap starts with step 1 that says first develop treatment goals. When you have your treatment goals, then review historic data and identify treatment needs. Only then, when you have this background information, start thinking about testing. And start with bench scale testing because it's much easier. Here you have 2 options, so you can do batch adsorption tests or isotherms test, and the other option is to do rapid small scale column tests. After you are done with the bench scale studies, then go on step 4 and think about pilot studies. And eventually, when you have all of that, you are in your final step where you can finalize your design and think about full-scale construction. And general takeaway from this roadmap is that there is no ideal type of testing, because each one can give you some good information, but at the same time, there is a list of limitations and boundaries, and that's why combination of testing is what is the best way to go with. So just for a moment, I will take a step back here and observe that roadmap didn't mention similarity approach, which is actually most common justification for not doing technology testing. This approach is generally acceptable, but not realistic at this moment for PFAS, because we just don't have enough information. And this approach requires first comparable water quality, and then comparable or scale flexible operation impact analysis. So to demonstrate issue with this, I gave here 3 examples with facilities that have production of 50 million gallons a day, 2 million gallons a day, and 0.01 million gallons a day. So these facilities are so different that using similarity at the very least will require justifications to manage differences in scale, co-contaminants, and many treatment processes, and each one can honestly result in mistakes. So this is not something that ADQ recommends for PFAS. And let's talk now about pilot testing. Even though this is not the first on the roadmap, I'm starting with this because it is the most conservative method to confirm treatment performance. As a result of this testing, you can get a bunch of good results, but it is also important to define issues that do exist even here. So this type of testing is time consuming. So you probably have to plan that if you want pilot testing, you need additional year to do this. And this is because we are in PPT concentration and that volume is usually more than 50,000. Then it's not just that it's time consuming, it is cost intensive. And you are actually here doing very limited testing. So what you select here, for that you will get results. So it's very important how you plan for this, because only your results will be good only for preset hydraulic loading rate, empty bed contact time, for that selected media, and so on. So here, after you're done with this, you are very limited with the adjustments. So be very careful. And this is why this pilot testing is not the first one on the roadmap. So it really should come after you have a bunch of other information. Another type of testing is rapid small column tests, which is actually scaled down pilot testing, where you reduce empty bed contact time to shorten running time and get fast results. Again, here is a list of issues with this type of testing as well. So the first one is scale down adjustments. So you usually have to grind the media, and when you do that, you can affect kinetics. And I really see that, and have to say here that this is still considered to be very controversial, even though this type of testing is like for many decades around, and it showed to be good for PFAS, but also for many other contaminants. But still, somehow it seems that there is an issue with trust here. So, as I said, scale down approach is what makes this type of testing difficult. So you basically have to speed up breakthrough curve, but stay in some kinetic boundaries so that your results are still useful for full scale. So there are two options here, either to grind media and short empty bed contact time, and this is more common approach, or to skip grinding, and then your design has to be more careful. You design column to still meet hydraulic number requirements, run at lower empty bed contact time, but same hydraulic loading rate that you have at full scale, and then eventually predict performance at full scale with the help of pore surface diffusion model, about which we are going to talk later. It is also important again to mention that either approach requires that your testing is done in specific hydraulic numbers range. So you have to explore literature here and really do detailed planning before you start doing this type of testing. And next type of testing that I have here is isotherms. And this is the most simple media testing. So the purpose of this testing is really to get equilibrium parameters. So when you reach that equilibrium, you can make a comparison between maximum capacity between different media, and that way you can make that media selection. So when you have that media selection, you can really use that in many ways. I would say the best approach would be run isotherm testing before you start doing your pilot testing or rapid small column testing, because you can start with, let's say, 10 media. You can do isotherms for them and eventually select 3 or 5 that have highest capacity for your source, and then keep doing more complex testing with them. Beyond that, you can also use this this testing to collect Freundlich parameters that are very important for model approach. Basic testing protocol here is that you can vary adsorbent weight or PFAS concentration in constant volume of water. You have to have continuous constant mixing, very low, like 30 to 50 rotation per minute. You want to avoid attrition. And then the name is telling you, so it's isotherm, so you have to keep a constant temperature. If you have variation in temperature, your results won't be representative. Then beyond that, you have to keep a constant pH. So add buffer if needed here. Your pH has to be constant in order to get that isotherm curve. And then eventually you measure contaminant concentration in equilibrium. So when it comes to data analysis, you will plot your contaminant concentration in equilibrium on X, and on Y you will have a capacity, and here is the formula how you calculate that capacity. You will fit those data and you will get Freundlich isotherm. From that Freundlich isotherm, you will quantify 2 parameters, K or capacity, and 1/n that tells you about affinity. And I have more information here to show you. So here are some examples of isotherms recently done for 3 commercial GACs and 4 different PFAS compounds. So focus here on intercept and slope, because higher the intercept, that K, higher the capacity of your media is. And on the other side, lower the slope of that line is. It can be line if you do linear fitting on curve, or curve if you do non-linear fitting. But you are looking at the slope of that isotherm, and the lower the slope, more spontaneous your reaction or affinity is. So just knowing this, you can immediately see that removal of PFAS is favored by many materials. PFAS isotherms have lowest slope and highest intercept, and this is shown by these blue triangles. Unfortunately, without specific values given for Freundlich parameters here, it is difficult to say what is the best performing media and get some other conclusions. But even though these isotherms tests are very fast and can provide so many useful information, they're very sensitive. And that's why I listed here some best practices that may help you when doing this. So first, start with literature review and do back of envelope calculation. So looking at the literature, seeing that capacity and concentration in equilibrium, you can back calculate volume and weight of your media to test. It is good to work with high volume. I would say work with 1 liter here, because you will improve your accuracy. Then vary media for those different points, not the concentration. It's much easier. Then when you vary that media and you want to really to catch high range, it becomes very tricky to measure very low amount of media. So work with wet media, and then recalculate results based on moisture content of your media. Then if you still have issues, if you're working with very low concentration of PFAS, increase that, spike that water with additional PFAS. you will probably increase capacity. Your K may change, but trends will be the same. Then I mentioned before, pH is very important. So add buffer if needed, because you really want to be in plus minus 0.2 when you compare your initial pH and final pH, before adsorption tests and after. Then do slowly shaking, and don't go less than 3 days, because you really want to catch that equilibrium. And then you cannot exceed that. So the longer you keep it, the better it is, but also don't go too long, because you have to control many other things. So I would say that 3 days would be my first trial here. Then compare media performance only if tested in same conditions. So you cannot compare media performance if one test is done at one pH, the other one at the other, or initial concentration of PFAS was different, and so on. So be careful what you are comparing here. And then eventually linear fitting, it's much easier. So when you get these data, transform everything to logarithmic scale and fit data with linear Freundlich isotherm. And since we now cover details about isotherms, rapid small column tests, and pilot testing, here is a table published by AWWA that compares important aspects of these 3 validation options. So in addition to pros and cons associated with each of them, it is interesting to see trends in time requirements and costs associated with it. Because many assumptions are included here, my suggestion is to look at these not as absolute, but rather relative numbers, because still you can get understanding and see how these trends are changing, and see what you can afford, what type of testing, and how to plan for that. So next validation tool is modeling. So even though this is not testing approach, it still requires testing results in order to improve prediction. So modeling is the most flexible optimization tool, but on the other side, it has the lowest accuracy. We are talking here about ET-dot model. Specifically, this is a package ET-dot, and there you can find AD design, and under that pore surface diffusion model that you can use for PFAS predictions. It is very important that this is open source, so it is free of charge. Purpose of the model is it's more than one thing that you can get here. So really, in general, you can do media selection like with any other type of testing. But more importantly, model will help you to design and optimize your system. So you can do model at many different time levels. So you can do model before you do any kind of testing. So let's say you want to do rapid small column testing or pilot. It is really recommended to run this model and see what would be the most optimal, how to design that test, how to design that column. When can you expect to see breakthrough curve, and like compare different media and so on. So you can do that like at very early level in design, but you can also do that after you have some column testing or isotherm testing, and it can help you with the scale up and full scale optimization. Model can predict lead lag or parallel performance, predict replacement intervals or media use rates, can improve your cost estimates. And again, I mentioned before, if combined with rapid small column tests sometimes can help you to avoid grinding of media. Basic protocol here is to collect parameters for your adsorbent or media, because you need that for model input. Model has a database that has some typical media. I know that there information for Calgon F400, but not for everything. So if you want to run this model for some new media, you have to get some parameters. Then you have to collect your contaminant parameters. You should do isotherm testing to get K and 1/n. I know that some people collect this from the literature, but that's not really a good approach because you want this to be very specific for your water, for your source. Then it's good to do rapid small column tests that you can use then to calibrate model. And then you will run pore surface diffusion model and compare that, I said. So eventually you will have that calibration to compare your model prediction with the rapid small column test. When it comes to data analysis, it's all about the breakthrough curve. So you can vary operational parameters to optimize design or to optimize cost. And then don't forget, this is very important. So this is a model. So accuracy of your estimate will depend on your input parameters in your calibration. So if you look for these parameters in the literature and you don't do any kind of testing, that's the lowest accuracy. If you do isotherms and you get that K and 1/n, you are improving these predictions a lot. If you go step further and do rapid small column tests and compare that used for calibration of model, that's very good. And eventually, if you even have a pilot, then really that would be the best combo that you can do when doing your design. And here is the link where you can download ET-DOT software from EPA website together with video tutorial. So it has many good details. I really recommend to watch that. And there is also a link that can give you additional Python codes that you can use in order to simultaneously with the model, because model itself without Python codes, I think, does not support lead leg design, but with the Python codes, it can do that as well. And as I mentioned before, if you get some extra time at the end of the presentation, I will be happy to demonstrate how this model works. So finally, after testing, we are at ATC step, which should be straightforward if you completed all previous activities. For ATC, for PFAS treatment, you will have to submit application, design report, construction plans, startup plan, process monitoring plan, and O&M is recommended in this case because even though it's a requirement to be with AOC, still we are in very new area here, so it's better if you can provide that with ATC application. So these provided documents must be for final, not preliminary design, so that after approved, construction can start, and you can, after that is done, you can collect testing results in line with approved startup and process monitoring plan. So let's talk a little bit more about design report, because it is heart of any treatment project. I listed here at the very high level what information it shall provide. So design report should definitely explain rationale for the proposed treatment process. But if you're small system, your design also should say that you consider non-treatment options and explain why is that not feasible for you. Design report should provide testing results and anticipated treatment capacity. It should describe how the proposed treatment will be operated and monitored. And then it should address all waste streams. So you have to have a management option for each of them. Then you have to design, then your design report have to discuss estimated cost for treatment, but also like what is anticipated to be for O&M cost and how is that going to impact water rates. Eventually, it also has to explain project funding. And so just a few words more about this, like cost requirement. It's basically means that we cannot approve something that is not set up to achieve long-term compliance. So this compliance is also results of TMF capacity of system. So we know that treatment addition will increase TMF requirements. And that's why design report should explain if existing TMF capacity can afford that, or if not, elaborate on needed adjustments. And yeah, so just provide more information about that. So next one is startup plan that must be approved with ATC. And again, here I have a checklist. Again, on the high level, really listing what are the answers that your startup plan, on what questions you have to give answers with your startup plan. So you have to explain here how you're going to keep your equipment clean, how you are going to manage your media, how you are going to keep those containers, are they going to be on cool and dry place, how you're going to do disinfection of your equipment. Then after disinfection, you will have to rinse that equipment. Then you have to confirm total coliform negative samples for everything. Then this plan has to have explanation of how you're going to fill your vessels with the media and at the same time minimize, let's say, air bubbles. And then I mentioned that before, is this media going to be pre-rinsed or not? If not, how you're going to manage that with your startup? And then eventually how you're going to collect BACT samples and water quality samples to confirm that treatment objectives are met. Then we have O&M plan, or plan for current and future operators on how to operate the treatment plant. O&M shall specify treatment objectives. Then it should describe process monitoring scheme and have a list of contacts as well. So you have to know who to contact if you have a normal operation question or you have accidents. So you have to have a contact for equipment, but also for media support. And then very important O&M has to explain procedures. So what you do in case of normal operation, what you do in case of troubleshooting. And I will just list all of this because it's very important, like to give you idea what do we consider that should be here. So how you remove your media, and then after you remove, you fill up a new media. So how you are returning treatment vessels in the production. Then how you are doing, how you are collecting samples, but also what are you doing if you have BACT positive samples. So what is your O&M procedure in that case? What if you have biological fouling? Oops, sorry about this. So I said, what if you have biological fouling or premature breakthrough? Or what if you have some air in your media? Again, the next issue can be with the pressure drop. Something can simply fail, and you can even lose your media. And then we mentioned before, there is a chromatographic peaking that can happen with PFAS, but also other contaminants. So O&M really should provide answers on all of this. You have to have procedures in place, not only for normal operation, but also what should you do if there is an issue, how you troubleshoot your issues. Another plan is process monitoring plan that tells operator how to monitor treatment performance. And at the very basics, it should explain differences in manual grab samples and automatic sensors monitoring. So if you do manual sampling, you have to know what to sample, where, how often, but also make a difference what is analyzed with field test and what is analyzed in the lab. If you have sensors, you have to know all of that, but beyond that, you have to be aware if those sensors measurement is going to trigger your alert. So how you know that something is off? And then, like with any sensors, what's your calibration schedule here? Then if you have a small water system, you can focus your monitoring on that midpoint between lead and leg vessel. It will give you very good information. But if you have large water systems, then you have to do beyond that. So you really have to sample on many points on those different sampling ports to see, you know, how your mass transfer zone is moving. Then I mentioned before, you also have to know at any moment what's the volume that you treated so far with your media, because you have to plan and know when is the time to replace, and you cannot wait for breakthrough in order to order new media. It really has to be done ahead of time. And then what's the last thing that I have here? You have to have even distribution of water across multiple treatment trains. And of course, you can only be sure that you have that if you have flow meters and flow control. So after ATC is approved, construction can start and be followed by startup. In short, purpose of startup is to confirm treatment suitability in regards to approved design and regulations. So you do not come to ADQ for this step, because startup plan should be approved with ATC permit. Instead, you collect the startup data that you then submit with your AOC application. And then an AOC approval is final permitting step. And for that, you have to submit application as built and tests. And these documents should provide information about final design. So if you have some changes, you should provide justification. Be careful here, because rule says that you have to communicate any changes that you want to do after ATC is approved. You have to communicate that with ADQ. So if you don't do that, you are really, you know, questioning if your AOC is going to be approved or not. So communicate any changes before you do them. Then you have to provide that standard set of chlorination, bacti, and pressure results. And then what is now PFAS contaminant in your treated water. Other than that, if you are using GAC, you should show that you don't have arsenic in your effluent water. And if it's ion exchange, you should show that you don't have VOCs in effluent. Finally, to show that all these requirements that we talked about can be met, I have here local Arizona example for PFAS treatment that got ATC approval in 2019 and AOC in 2021, which means that is in operation for the last 2 years. So this system treats 2 million gallons a day, and they have elevated PFOA and PFOS concentration, and as well 1,4-dioxane. They also have a high sediment in their water. So their treatment train consists of strainers and bag filters to remove sediment. And then they have this UV AOP part to address 1,4-dioxane. So they're adding peroxide, and then they're having UV lamps. And after that, they have a total 4 vessels in basically 2 treatment trains. Each train is lead leg. GAC is in those vessels, and GAC is treating for PFAS, but also quenching that residual peroxide that is coming from UV AOP. So each vessel here has about 670 cubic foot of GAC. And then after that, they have a post-chlorination, and then the water is stored in storage tank. So it is interesting to note that approved design included 19 micron bag filters for sediment issue. But this was not sustainable for operation, and they did 2 adjustments after that. So they are now using 50 micron ones. So I wanted to mention this because even though accurate design is very important, it is realistic to expect that some minor changes will be needed over the time. But another very important aspect of design is media lifetime. And that's why I talked so much about the testing, because what they see is they're getting breakthrough on lead vessels after 2 years of operation. Just a quick calculation here. So if they have if they want to replace media in those 2 vessels, each one 760 cubic foot, and I put here $60 per cubic foot of media. Just for that, they need more than 80,000 just for media, without including replacement costs and other things. So also to mention here that when they do that, they will replace it in lead vessels, they will go in leg, and then leg will go to lead, but next replacement will be sooner because those leg vessels are already in use for the last 2 years. And one more thing that you should not forget is that supply chain for GAC is not great. I assume that is the same for ion exchange, but I unfortunately didn't check before this. But what I know is that they will have to wait minimum 6 months to get this media replacement. So this just further amplifies the importance of testing to provide accurate media lifetime, but also non-compliance sampling so that it gives you that safety and time to plan for all of these issues. And the last topic for today is point of use and point of entry units and their current compliance limitations. So while approval process is similar to centralized treatment, acceptance of point of use and point of entry units is heavily based on NSF certification testing, which allows that plug and play approach. However, for PFAS specifically, these devices shall not be considered a compliance option until NSF standards are aligned with the MCL. So beyond this limitation, that will probably be addressed in recent future, it is important to mention that this type of treatment should be limited to 25 connections due to cost-benefit analysis and decentralized O&M cost. And I think that you also saw that in the cost analysis that Tom showed before. So because we see many deficiencies with this type of treatment, even for other contaminants, it is highly recommended to always coordinate with ADQ before you start planning for this. And here are a few additional details about NSF certification and why is that limiting current permitting of point of use and point of entry for compliance. It is because currently on the market, we mostly have units certified to 70 ppt of combined PFAS in effluent. You know that the proposed regulation is for 4, so difference is huge. So what the NSF did, well, in 2022, they did updated standards. However, at that time, they really relied on previous health advisories, and now if someone has certification against that new standard, it will target 20 ppt of PFAS in effluent, and testing will not include GenX. So basically, we don't have NSF certification in line with proposed regulation, and the whole market is in transition between these two phases. So these are all the reasons why we don't accept this at the moment. So next, after that, I wanted to give you more information how to search for these, and then eventually wait for these updates. So there are 2 agencies that are testing for PFAS so far. So it's NSF International and Water Quality Association. There are 2 standards, either 53, NSF 53 or NSF 58. And then very important is standard means nothing if you don't see the claim. So these devices can be NSF 53 or 58 certified, but that doesn't necessarily mean that they have testing results for PFAS. So be very careful here. These are in the slide. You will see 2 links for databases to check what is certified and for what, but don't expect that anything is certified so far on to propose regulation, because simply standard still didn't address that. And then eventually there is a question that I get very frequently, and that's are Brita filters certified for PFAS removal? Well, answer is no, they are not certified and there is no claim. So they may be removing some PFAS, but there are no testing results to support that. And in addition to this and other PFAS trainings that are coming, I want to say that ADQ is working on few documents to further support all this PFAS effort. And here is a list of documents that are coming soon from us. So you can expect to find selection and permitting guidance documents for centralized treatment, but also for point of use and point of entry. And then I mentioned before, we are working on the updates on the existing EPA calculators, just to make them more Arizona specific. But you can run these calculators for both non-treatment and treatment options for PFAS. And then we are also working on protocols, or let's say best practices that will help you to run tests, including isotherms, rapid small column tests, pilots, and also how to run ET-DOT model. Then we are also working on decision trees, again, to help with the selection for both non-treatment and treatment selection. And then eventually we will we will in the future work on like try to provide a list of facilities and corresponding cost for residual stream disposal. We will probably wait for final rule to be in the place for this, but this probably will include Arizona, but also go on neighboring states. And I think, yeah, this is the last slide of my presentation. So here is my contact email in case that you have any additional question after this training. And I mentioned before, so depending on the time, we may also do model simulation, but we have to plan for time for questions. So can someone please tell me what's our next step?
Yasmin, I think we're good on time. So if you want to spend a bit of time with your model simulation, that's great. It's just 11 o'clock and we'll try to switch over to questions by 11:30.
Okay, sounds good. I think that I will not need half an hour, but let me get started here.
Okay.
So you can still see my screen, correct? Yeah.
Yes, that's correct.
Okay, I'm putting this down, and I will run a model from here. But first, I want to show you some results that I received from let's say X facility. So they have they are on groundwater, and their source has both PFOA and PFOS. So recently they started to see like after many times of non-detects, they started to see both of these species in their effluent after lead vessels. And I thought that it would be interesting to see this graph now showing bed volume treated, and then here effluent divided by influent concentration. So if you see this, I will now try to run a model and to see how close we can go with the model estimate, and what is crucial to get something similar with this data that we see from field. So again, here, even though that PFOA concentration is lower in influent for this system, they saw breakthrough before than what they saw for PFOS, simply because any kind of media is going to remove PFOS better than PFOA. So remember this, they're about like 1,040, no, sorry, 140,000 here for PFOA here. And then they reached up to 0.3 here. And then for PFOS, they started to see detects at 160,000. So I will keep this here. We can open this again, but let's start with the model and try to simulate this system. I mentioned before, so there is a detailed like a video tutorial provided by EPA, and you can access that link from the presentation. But here I will just, I will really not go into details, but more like show you how it really look like, and what you can change and how you can play with this. So here I have ET-DOT programs. It's a package of programs, but I'm going on AD Design S. And of course, it's moving to different screen, but this is what you will see first. You click continue here, again, moving on to another screen. And then when you click continue, you will see a screen like this. And this is basically your screen for input information. First thing that you can change here is pressure and temperature of your water, but for the purpose of this training, I'm not going to do that. Then you can put your compounds here, and then here are here is how you want to simulate this. So if you look at this, if you keep like this, you will get simulation for 174 days, which is not good in our case, because this system facility that I got results from, they saw breakthrough, I don't know, about after 600 days or so. And then here you can change some other collocation points, but you really don't do this if you don't have to. This is more about playing with that model background. It's not going to affect your results, but sometimes model can be stuck and you have to change this. But you are really not playing with the output, more like helping model to give you those results. And then on the right side, you put basically information about your system. So about your columns, flow rate, and so on. So this is about like system information. And then here it's adsorbent database. So here for this training, we will use Calgon F400, and you have all the information. Other than that, you can go to database and see their information for other few materials, but if you want to put something that is specific and it's not included here, you are more than welcome to get these information and change them and save that new adsorbent properties in your database. So let me get started here. So I'm going to add first compound, and it's going to be PFAS. Saying PFAS, molecular weight, here I have 500 milligrams per millimole. Then I'm skipping this, so don't be confused here. You will see all the detailed instruction in the video tutorial, but basically it is a difference if you are running adsorption in a liquid or gas phase. In the liquid, you need only few information. So if you are missing something and you cannot change that here, that is going to be okay because you are running in liquid phase. So you need molecular weight, you need initial concentration. Here, be careful. The lowest one that you can select here is ppb. So I'm selecting ppb and then putting, because they have 45.8 ppt, it's going to be like this in ppb. I'm skipping liquid density, solubility, and other things. And then I'm coming here to Freundlich parameters. So model is asking me for K and 1/n. This system never did isotherms, so I don't have this real data. Instead, I checked the literature and I pulled out some estimates for those two, and I'm putting them here. But again, this is not a good way to do that. So it can help now with the simulation, but you really want to do isotherms and to see for that media in your water, what is K, what is 1/n. These are very important parameters and can change many things. So be careful there. You can do isotherms in 7 days. So it's really worth of doing that. So again, be careful about units. So this one is what I'm selecting here. And here I will go with 500. And here 1/n, I will go with 1. And then you see at the moment when I put 1, it changed this because 1/n is part of this. So it's better always to do what is 1/n first and then change this to 500. So I will say OK here. And I just want to show you beyond these properties, you can also go here and change kinetic properties. But if you don't have input, a program will populate this for you. Again, you don't have to go with this. If you know that this is different, you have ability to change that. But I'm not going to do that now. So I have a PFOS, I added that, it's here. Now I want to add PFOA. So I'm adding PFOA, and then for PFOA, I have different molecular weight and different concentration, which is going to be 0.064. Okay, I'm not changing anything else here. And then going again on Freundlich, I'm also putting 1/n here to be 1. But for K, I'm putting lower value, so I will go with 440. Again, this is just assumption, and it's not the way to do that. So you should get this with your experiments and then input here. Or if you are looking in the literature, it really has to be, if someone tested this, that water quality has to be similar to what you have in order to be able to use those parameters. So I'm saving this, and now I have PFOS and PFOA here. Now I will switch to a column here. So bed length for this system is 5.9. Diameter, again, I will change unit, is going to be 12. And then for mass, I will put pounds, and it is calculating already what I have, but yeah, it's about 20,000. Then yeah, be here, it didn't say one thing. So how is program able to calculate that? It's because, you know, you are giving length of diameter and diameter of your column. So based on volume for your media and the density for this specific adsorbent that is selected here, program is going to calculate the bed mass. But when you are putting parameters here, length, be careful to put only what is for your adsorbent, not what you have for your supporting material or the full length of your vessel, which also has, you know, extra space for backwashing and so on. So only parameters for your adsorbent. And then here, so this is the empty bed contact time. Sorry, I didn't change flow rate. In their case, it is 600. And then when you change that, program is also calculating empty bed contact time for you. So don't be surprised here. They use GAC and empty bed contact time. This is only for lead vessels. So their full, like total empty bed contact time is 16 point something. This is only, we are doing lead vessels, because we saw that they are having a breakthrough in lead vessels. Here, we are not going to change anything about the adsorbent, but let me show you now, like, what are the options. So this is what database has. So it has basically 5 manufacturers, and you can select different media. Again, doesn't mean that this is what you need, but you can always add new adsorbent. So when we are done with that, I'm going to change here. I want model to run for 700 days to show me what's going on over 700. Well, be careful here, because if I put here 700, it will say it's impossible. Why? Because this is what is controlling that, and it says it's too many points for this model. So I have to increase this here to eventually reduce this number of points. So I will say time step 2. I will say, you know, start with displaying everything after 200 days, because I know that they don't have detects in a first 200 days. Oops. Oh, it seems that then I have to go first here, and then I can go and say here 200. So after we have all of this, then you have to run the model. So you can select only one contaminant, or you can select all of them. So I'm going to select both of them and go here, run pore surface diffusion model. It's telling me it's done. So I go to results here, and this is what I see. So this is not great representation, which means that you have to go back and do some kind of adjustments. But you can see that it's estimating here like that this concentration of both PFOS and PFOA are going to start going up about after 100,000 bed volumes. So model is showing us that PFOA is going to have a faster breakthrough than PFOS, and that makes sense. That's what we saw with our results as well. Now, really, to get more information, we would have to go back and just like edit some other parameters. But other than that, you can change here if you want to see this in bed volume treated, or you want to see in time, or volume treated by weight of media. And then here you can also change what you want to see on y-axis. So many options here. Again, to see this better, you would not change like these column parameters, your sorbent or your media parameters or contaminant parameters. You would go here and play with this total runtime, first point displayed, and time step. So that will help you to observe your results in a better way. But again, this is just a short simulation to show you what the possibilities are. I would recommend you to watch a tutorial by EPA and then download this software and basically start playing with that. And that's the only way to see where you need help. The next step here would be definitely to export this data and to compare that with the real data that we have from this facility. But again, this is only simulation, and it might be that when I put here like parameters for PFOS and PFOA, it might be that this is not good. So going further here, it really makes no sense because this is just my estimate, not the results that I got after testing this. It is very important to have these correct, because if you just change this slightly, especially 1 over n, your breakthrough is going to change significantly. And that is what I have for this simulation. I think that we can go on questions now, and then if yeah, maybe it will be easier to go on that and then answer everything that you additionally want to know.
Hello, everyone. Just remember, if you have questions, please put them in the questions pane in the webinar, and we will go over those and see about getting some answers. All right, so we have a question from Shrikant. And they're asking, what is the current stand of ADEQ for regulating PFAS in drinking water, wastewater plants, both liquids and sludge, pending regulations from EPA? What would you suggest the municipal wastewater treatment plants to consider from the ADEQ perspective? And we'll have about a half hour to answer your questions. We might have a little bit more just because Yasmina finished up a bit early. But Yasmina, if you have an answer to that question, feel free to go ahead.
Yeah, sure. So I will try to answer, but I just want you to know that really the focus of this training was not like a regulatory status, because as you know, we are all waiting for that final rule. So what ADQ is doing is really following EPA recommendations. And my presentation today was about what if is that final rule, what you should do if you are planning for treatment, how you can address everything that you have to do in order to do that, to meet that minimum design requirements. So other than following really what is coming from EPA, I cannot give any more specific information in terms of this question.
All right, we have another question from Robert. Will ADEQ or EPA consider water utilities to be exempt from CERCLA as it relates to being a hazardous waste generator, seeing as it is removing the human-created contaminant from the environment and was not the initial polluter?
Again, so I'm really not qualified to answer on this, because we are just waiting to get to see those final rules in order to say where we stand and what we can allow and what we cannot. So all my presentation today was what I wanted to try to say is, this is something that is proposed, so plan for that. We always have with the regulations, it's always possible to have some alternative designs and approach, and I really don't know how is this going to be in this case. And it's always it's always case specific. So again, I appreciate question, but I cannot give you any specifics at the moment.
All right, another question from Robert. I think it pertained to a slide on your presentation, Yasmina. Is it NSF 53 and 58 or NSF 53 or 58? I'm not sure, maybe he repeated the question. Is it NSF 53 or 58?
No, so what we have for PFAS removal, it's two standards. It's so device can be certified by NSF against NSF 53 or NSF 58. So 58 is specifically for reverse osmosis. So if point of use is reverse osmosis based, and vendor wants to do certification, they will test that against NSF 58. On the other side, their point of views that have, I would say, they usually do combo of adsorption media. So they do the mix of ion exchange and GAC. And if that's the type of point of views, then they can certify those units against NSF 53. The issue with both standards is that they are targeting at the moment that latest revision from 2022 is targeting 20 ppt in effluent, and we know that that is not in line with the proposed regulation. So before that is adjusted, we cannot accept those applications. Again, this is what I'm talking is about permitting and compliance, but ADQ is not permitting anything behind the service connection. So if you want to install in your own house, if you want to install point of use, you can do that. You don't need permit for that. And you should definitely look for something that is certified. So even though it's not certified for proposed MCL, it is better to be certified for something than nothing.
All right. Moving on. What do you think the regulatory future is for PFAS in wastewater, particularly where infiltration basins are used for effluent disposal?
Well, this is similar to one of previous questions. I really don't know what regulation is going to bring to us. But what we know is that PFAS is persistent, and why we have these issues, all of this is because of that persistent nature. So if we allow something to circulate in the nature, I don't see how we are going to resolve the issues. But again, we are just waiting for official regulation to follow here.
Hey, Yasmina, it's Jason. Good morning. Thank you for the presentation. I've been answering those questions. As the EPA regulations are finalized and updated, more information will be made available. That's all. That's the best answer we can give right now.
All right, back to a question that pertains to your model, Yasmina. Can the model be used to compare results from RSSCTs?
Yes, I mentioned that a few times. So you will run a model based on isotherms data. And then you can export those data and compare that with the rapid small column test results. And that can really be your calibration. So you can see if in the model, the beauty is that you can really change everything. So all your input parameters can be like those that you had in your rapid small column scale test. And then when you compare them, it should be really overlapping. If not, that tells you that something is off. But comparing a rapid small column test with the results with the model results, it's a great approach. But I would just say that it's very critical to have isotherms data, because having those two and seeing non-alignment, you will not be sure what might be off. And it's probably that your isotherms parameters are not good. So I would say do isotherms, do model, rapid small column tests, compare all of them and see where you are, and then know if you need something additional or you are ready for your design.
All right, another question for you, Yasmina. Do you know if surfactants associated with metal plating prep may be a source of PFAS in wastewater influent, assuming poor pre-treatment? Sorry.
I'm not sure for that. I would have to check. Yeah, I really don't know. So if whoever sent the question, if you want to send me email, I can search for that, but that's not something that I know at the moment. I'm sorry.
All right. And then a few questions. Will the slides be available post-training? They're actually available right now in the handout section of the webinar, so you're welcome to access them from there. And then another question that was asked a little bit later on, is the webinar being recorded, and will it be able to be made available to attendees? The answer is yes, the presentation is being recorded and will be available on our website, azdeq.gov, or on ADEQ YouTube channel. And then if you look in the questions, that YouTube channel link is there as well. Going back to questions pertaining to the presentation, let's see. I don't know if you'll be able to answer this. It seems to be a continuation of the question we just talked about, Yasmina. If so, do you know which specific constituents may be associated with the same? So that might be something you can get back to with them if they reach out.
I'm sorry, I didn't understand. So what constituent can be associated with what?
I think the question, do you know if surfactants associated with metal plating prep may be a source of PFAS in wastewater influent, assuming poor treatment? I think the question was just continued on And if so, do you know which specific constituents may be associated with the same?
Okay, I will try to look for that.
That sounds great. I'm not seeing any other questions.
We did have 2 questions that came in through email. I know my audio is a bit staticky, but perhaps you could read those, Hannah. They're in our Google Meet chat.
Yes, absolutely.
You.
Let's go ahead and take a look. So those questions are: water that enters homes from the city could be free of PFAS, but could PFAS leach from, say, in-house plumbing equipment like O-rings, rubber valves, flexible tubings, etc., and end up in tap water effluents?
Yeah, I believe that our knowledge is not really on that level to answer on this. So I don't have any internal information. You know, what is in literature is available to both you and me. I don't have any additional information here. You know, you see that it's basically everywhere, but in terms of specifically to this question, I really don't know.
Yeah, this is Tom. I think I could jump in on this. You know, it could have some PFAS in it initially that could leach off, but generally what we see is that over a short period of time it leaches pretty quickly and then is stable. For instance, and why I mentioned that is that oftentimes when we're sampling at facilities, they might have some type of Teflon sampling, you know, tubing and things along that line. And if it's been in use for a fair bit of time and it does not seem to leach out PFAS that we've seen when we take samples from it. So if it was, you know, just brand new installed, you know, with Teflon tape and all that, you know, maybe you might see it, but over time, we've not seen it. When it's always best to avoid those materials when sampling, but we haven't seen it really influence the results if it's been there for some time.
Okay, and then the last question: what do you think are major knowledge gaps regarding GAC regeneration that exist in the industry? How well are the regenerated GAC studied? Are they studied to see how much PFAS have been removed, how long they can be used, or how many cycles of adsorption regeneration could there be?
Yeah, I can jump in on that one. So I think the knowledge gaps on GAC regeneration is largely with regard to what's the impact of a full-scale facility and the design and flow rates around such, and how does it differ from bench and pilot type situations. I think with regard to regenerated GAC, I think it's pretty well thought that once you reactivate a carbon, that if there's any PFAS left on the carbon after reactivation, it's pretty well bound to the point where when you put it back online, it's not going to leach off because it's stuck so well. And so we don't see it in reactivated carbon coming off of beds. Now, so I'm pretty confident that once reactivated, it would be all right to reuse that carbon. And secondly, if you regenerate it numerous times, it doesn't seem to change that property. What you would see if you went 20 different, you know, over 20 years, what you would see is your carbon would change in terms of pore structure. So you might lose some of your finer pores, and you might end up with a carbon that's kind of different than one you started with. And so it wouldn't be necessarily with regard to is PFAS on that carbon. You'd be more interested in if the carbon's pore structure has changed to a point where the contaminant that you're interested in isn't absorbing as well. that would be more of a concern than if there was a contaminant on the carbon that just builds up time after time after time. And for what we've seen, very, very, in at least one instance that's been going on for a long, long time, we don't see the change in pore structure impacting PFAS absorption too much to the point where the carbon has to be replaced. So I think we're in pretty good shape there.
I would just like to add here that ADQ started communication with Calgon Carbon because they're kind of local here. So we really hope to get more information from them. We are also planning like a vendors workshop that is going to be, I think, in February. So they are going to be there, and you're more than welcome to come and ask your questions. But I also hope that they will provide more information. So what I'm concerned about is like, is there any threshold here for that regeneration? Because we have so many small systems, and I think that you know, it might be issue if you are so small, if your volume of spent GAC is not high enough. Are they willing to regenerate that? And you know, like eventually, what is that cost benefit analysis? Is there a threshold that says, you know, if you generate less than this, then it just makes no sense for you to think about regeneration. But again, we hope to have these answers in the future. But we are aware of many unknowns, and we are working on that.
All right, we have a few folks who are having trouble seeing where the handout section are, so please see the current slide. If you go to that orange arrow and open that window up, you should have it listed as one of your panes you can drop down. If you're having issues still and you can't get to it, there might be a way we can send you the slides if you contact us. Let me go ahead and ask a couple new questions that popped up. If carbon is listed as a RCRA, hazardous waste, and it is sent to a regeneration facility classified to regenerate a hazardous waste, can it be placed back in a potable water application?
So this is something that we hope to get more specific answer from Calgon Carbon. So according to EPA guidance, you can regenerate GAC and then reuse that for drinking water. But there are some other questions, you know. For example, I would have to know, like, if I'm doing review and you are telling me that you're going to use GAC and then regenerate that, in order to permit something like that, I would really have to know if that regenerated GAC is going to be NSF 61 certified or not. And if not, because it might be not, because you know, when you change final regulation, then you have to wait for all the others to catch up. So if it's not, then it has to be some kind of justification explaining, you know, it's not, but this is how we know that this is acceptable. So
Yeah.
that. Mm-hmm.
And I think it depends on how the rules come out with the exemptions with the rules. But you know, sometimes a utility in situations with carbon manufacturer, they'll accept the carbon back and give them then a cut rate for replacement of that carbon as virgin carbon. So they would return virgin carbon to the utility. And if you think about it, as soon as you take out the carbon, you have to replace it immediately anyway. So it's usually that kind of trading off of carbons. And sometimes, depending on how the rules play out, the activated carbon company could reuse that carbon for other purposes other than potable water, so like industrial uses and such. So they could find another use for it that's not necessarily potable. So sometimes agreements with utilities take that into account, and you get some sort of cut rate from the carbon manufacturer.
All right, I'm not seeing any other questions popping up regarding the presentation. Again, with the handouts, if you're not seeing the handout section, it might be just a different form of viewing. If you're viewing from a cell phone or a tablet, sometimes they don't show up, but just go ahead and email Sarah and we'll get those documents to you. All right, so thank you again. I'm not seeing any more questions, but if you do have further questions, you're welcome to reach back out to us via email. So thank you very much to our speakers and to everyone for joining us today and for all your questions. We hope you found it useful. Presentations are available in the handout section. And again, if you can't view the handout section, just reach out. We'll get that to you. The recording will be posted to ADEQ's YouTube channel in the next couple of weeks. If you have any follow-up questions for our speakers, their email addresses are on the slide. And if you have any ideas for future training topics on PFAS, please send them to Sarah. Her email is also on the slide. Additionally, ADEQ is holding an online workshop for water system operators to learn about PFAS regulations, sampling, treatment, and funding. That's on Monday, November 6th from 8 a.m. to noon, online only. You can register by following the link shown on this slide. Thank you again.